There's no audio in the video conference.
the whole group into user space, because you could potentially influence other devices then and maybe break things, right?
So we have already got a series merge to fix that. It's called the Iommu ownership series.
Okay.
So what we've done there is we've created this concept of ownership. So when you take ownership effectively of the group, because the group is a security object. And when you take that ownership, it excludes anyone else from using the group that's not in your kind of trusted set.
Okay.
And that was one of the big important series to make this all work that got merged. It effectively lowered the model that Vfio used for ownership and isolation and put it directly in the core code, right into the driver core, in fact. And now everybody participates equally. So if you're a device driver and you want to use Iommu special features, you can do that, and you participate in the same ownership model that Vfio is using.
Okay, so you still have the same, like you still basically do groups, you still claim a group, you just do that all via device API. Okay,
yeah,
that's fine.
Yeah.
Cool.
So that everybody can go and see that. I see a lot of stuff on the chat here.
They have audio.
They have audio. Okay.
So we call the end of your question.
Ooh, awesome.
Would anyone on the remote users like to speak? I can go through the chat here.
Yeah, it's just a discussion about audio and me attempting to live text what Alex was
Okay.
So can you start again now?
saying.
Yeah, can we start again?
We've got enough time almost. So anybody else in the room? I saw there were some other hands earlier. Yeah.
All right. I have a question on the dirty bit tracking. So we right now have this devices with the migration region support added, where you can provide the dirty bit tracking if required. And now with Iommu, if the hardware supports the dirty bits, we have another mode of tracking the pages. So how we will select which one, or what is the policy is going to be like if we have both in a system, a pass-through device has both in
Right.
place.
So I think what you're asking is, like what I talked about earlier, is the Vfio has a dirty tracking API that's for called the device-specific tracker. And one of the points of the design was to make the policy decision of which one gets used a user space choice. So user space will be able to discover that the system Iommu supports it. It will be able to discover that the device supports it, and then it gets to pick. Do I want to use the device tracker? Do I want to use the user space tracker? And our feeling is that that's going to be based very much on a performance analysis, probably unique to each kind of configuration. We're not sure what kind of performance we'll get out of the system Iommus on every platform right now, nor are we quite sure what kind of performance we'll get out of the device trackers. This technology is all really new. And until somebody sits down and does a whole bunch of performance work, we just don't know which is the right one to use in any case. So for the moment, at least from a kernel perspective, the policy is going to be shifted to user space. User space policy is usually our thing anyway.
So is there any work ongoing to try using Vfio and using Iommu FD outside of Vfios, so to prove that it's sufficient for other use cases?
Nobody's invested in that at this moment. We're pretty confident though, because you can look at VDPA and you can look at their ioctal interface, and it's the same thing. Right? It's map, unmap, and a few other simple things. I have had in the back of my head, I would like to connect this to RDMA, but to make that useful, I need PASIT support. That's a convenient way to increment or implement PASIT support for RDMA, and right at this instant, no hardware exists for that, although people are starting to experiment with it. So we're really ahead of this, where the hardware is in a lot of these topics, in part because Linux has been a bit behind. I should probably say that other operating systems have gotten a lot further along implementing all of this stuff. So in that regard, we're lagging a lot, but at the same time, the hardware ecosystem is also kind of tardy.
Yeah, it would be great if someone could actually try using it in another use case, so that we don't end up in a situation where we have a user space interface which does not fit future purposes, right? So actually have the proof that we got the interface at least somewhat right, that it does not,
okay,
that we don't need to overthrow it in 5 years or so.
Yes. Well, that would be bad. VDPA would be a good one to see, or at least mapped out how it would work. I can start to talk to Jason and a few other people and see if maybe we could make an experiment. The trouble is no one who's been working on this is really that familiar with the VDPA world or how to even set it up. But I think we can probably work something out. I would like that also. The thing that makes me feel pretty confident that the API will at least last is that the API matches what we've had in Vfio for the last 15 years, and it matches what the Iommu subsystem, like Iommu domain ops is relatively exporting. So it's not too radical. I get a little worried when we go into the new features, because the new features are, like I said, we're ahead of the hardware a little bit. We don't really know exactly how things are going to shake out in 10 years, but the API has been designed to be extendable and kind of tolerate change going forward. But that's a good point. Thank you. Anyone else? Got another catch box here.
Hey, Jason. This is Kevin.
I have one more question on the nested translation. I see some chemo with support for based on IOMMFT based nested translation in the parallel GitHub branches, but couldn't find anything that actually supports the ARM version of it, like the dual stage setup and the page response path. So is that you have any update, or Eric is the person? I don't know.
Eric and Nicolin have been working on the ARM stuff, kind of again on top of IOMFT, and they have all kinds of GitHub branches. I haven't taken a careful look at exactly what it is. Maybe if one of them is on the chat, they could talk.
Yeah, so Eric speaking. So maybe Nicolin also is.
Kevin, can you
is
talk?
It here?
Do I have to do something to allow them to talk?
You should be able to enable your microphone and speakers, Kevin.
Can you hear me?
Eric has appeared. Eric?
Yeah, Eric, can you hear me? Hello?
Kevin?
We can hear you, Eric. I'm not sure if the
okay.
can hear you, but remote join is definitely can hear
I
you.
don't see I don't see him up here.
Yeah, so I can hear you too. So can you hear me?
Oh, there he is.
I'm not entirely sure if the room can
Okay,
hear us.
so the audio seems to be very much one way, and I see in the chat here that other people can hear Eric speaking, so we can't hear him in the room, unfortunately.
Hello, can you hear me?
Yeah, I can hear you. Eric speaking.
Yeah, Eric, I can hear you, but seems not in the room, not by the phone.
Yeah, I know that.
Okay.
That's a weird situation again. Okay, so maybe basically I can write my comment in the chat instead.
Okay, well we're working something out here. Okay, go ahead, Eric. We'll see how this works.
Okay, so I just wanted to confirm that Nicolin, Ken, and I have a proto working for nested, so there is a lot of echo. And so basically this is at the stage of proof of concept. Can you hear me? So it's terrible with respect to the echo.
I think typing it might be better.
I think so. Ooh, we're doing it our best, Scott. Yes, if you type it, I will read it for you. Thank you.
Okay, so we have something working, but it is at the state of proof of concept right now.
What you'd like to say, I'll free will here about the kind of plan for the nested translation. the general idea, so nested translation is basically delegating page tables to user space. So you can put an IO page table inside a user space page controlled by a user space process, and the Iommu hardware will read the first level of IOVA translation from the user space page table, and then it will go to a second page table that's owned by the kernel to convert it to a final physical address. So user space is constrained by the kernel-owned page table, so it can't just point to any piece of random memory. So in the Iommu FD model, we explicitly model each of these layers. So you have the kernel-owned page table modeled as a hardware IOAS with the map unmap, and then you have the user space page table modeled as a hardware page table object, as it's called, that points to the hardware-specific page table layout and the hardware-specific format. And then when you get to something like Vfio, you say, hey, Vfio, go use that hardware page table format. And it ends up in the kernel as an Iommu domain that wraps the user space page table setup. So from the kernel perspective, everything becomes an Iommu domain, and we're just attaching different weird special Iommu domains into all the places. I think you had asked about PRI as well. I don't know for sure. Maybe Eric will comment on the chat, but I don't know if they've done it for ARM just yet. I've been encouraging everyone to kind of split their work up into chunks. So like the user space page table chunk is a discrete unit and has its kind of its own discrete API, and then PRI is sort of another set of APIs. If we don't do that, it really blows up. You're starting to look at a lot of complicated APIs, and the APIs are very complicated when you start to get into some of this stuff.
A couple of questions in the chat.
Yeah, I'm trying to go. As you commented, Nested is working on ARM. That's great.
There was a question about the complet layer, whether it's what's the point of the complet layer if it's not complet?
So what we've been using it for is testing and development. Like it does work, right? It's like 90%, maybe 95% good. But as I said, it's not bug for bug compatibility. So if you have scenarios where you're relying on the bugs, and Alex definitely has a few scenarios, some real scenarios in mind, it's not going to be compatible. The question was, should we finish the 5%, or should we leave it as a development tool? Or the other model I had is kind of in between, where an application like, let's say, DPDK can opt into Iommu UFD. It can do all of its testing. It can decide that the 95% coverage is good enough for it, and it can just put 3 lines in its code, and it's moved to the new interface. So we kind of have these 3 possible uses for it. I don't know what is the right thing for the community. The thing that makes me kind of the least happy about all of this work is we end up with Iommu UFD as kind of duplicate code compared to Vfio. It's not actually duplicate because it's all very different to support the new requirements with the pinning, but it overlaps so much. It's just unfortunate we keep them the same. I had hoped one of my other plans was that we could replace the internals of Vfio and keep the container interface. But that was before I knew about these details about the page pinning and the other things that Alex has brought up, because they go deep down into the data structures. Like pinning, how you account for pages is kind of fundamental. Anyway, I think I've reached the end of my time. Thank you, everyone.
Yeah, time to wrap up. Thanks. I think if there are more questions, we can take that offline and discuss it in one of the hack rooms. Next session is from James, who will talk about cooperative DMA in a memory oversubscribed environment.
Cool, thanks. How do I switch slide thing here?
Cool. Hey, James, you're going to need this.
I need that. I think you are out of here. Okay, cool. Upload it. Right. interesting one too. Okay. Great. Hi, good morning, everyone. I'm James. I'm a kernel engineer working at EC2, and the discussion that I'd like to have today is around memory over subscription when we're doing PCI device assignment to virtual machines. Specifically looking at a way to do memory over subscription while not depending on more advanced hardware techniques such as PRI, but trying to use a lightweight cooperative technique to be able to do memory over subscription. So roughly, we're going to look at overview of the current state of device assignment and memory over subscription, then discuss two aspects of the proposal, which is basically making Iommu page tables dynamic by hooking them into MMU notifiers, and also adding this lightweight guest cooperative technique to ensure that pages are always resident before the device attempts a DMA transaction. So the way that DMA-capable PCI devices are assigned today are and this walks as was in the Iommu FD presentation, this walks the whole user space address range of the VMA which is being assigned to the device, pins all of that memory, so faults it all in, and sets up the Iommu page tables when the IO control is invoked. So it sets it up all up front. As far as I can tell, this is done for two main reasons. The one is simplicity, so you just have to set up your Iommu page tables once and then again. You're never going to encounter nothing called So there is prior art, again, as mentioned in the Iommu FD talk here, around address translation, service, and page request interface for device faults. But PRI support seems limited. It doesn't seem that well plumbed into Vfio at the moment, and I'm just also not sure how prolific it is in hardware. It still seems quite exotic. And so it seems kind of tailored to Intel graphics at the moment, and it'll likely be a while before it becomes more broadly supported. The other relevant hardware technique is around shared virtual addressing, which was also mentioned in Iommu FD, where the CPU and Iommu share the same page tables. And this is great if you've got PRI support, but if you don't, you actually probably don't want to share those page tables exactly. I think it might be preferable to actually modify them in a controlled sequence, keep them independent, and we'll get to that a little bit later. So in summary, there are lots of devices out there, some which support PRI and can take page faults, but most don't. And I'm looking here for a software technique that doesn't rely on these hardware functionality in order to be able to do memory over subscription. So the first part of this is about how we make the Iommu page tables dynamic, similar to what we get with shared virtual addressing. So I'm suggesting a new IO control, Vfio map DMA unpinned, and this basically does no allocation up front. It just sets up the Vfio data structures and assigns PCI bars and such, but doesn't pre-fault any addresses. It doesn't set up Iommu page tables. Vfio would then hook into MMU notifiers so that as the user space page tables are updated, Vfio would get notified via the change PTE or invalidate range callbacks, and then Vfio could come along and make the same modifications to the Iommu page tables to keep them in sync. There are some challenges with this. At the moment, change PTE is not used that extensively. It seems to only be used for copy on write faults. And we need to be very strict about these MMU notifiers now. If we're basically driving Iommu page table updates, we need to always notify so that Vfio can keep its page tables in sync. And similarly, we should never call the invalidate notifier spuriously, because we'll actually be tearing down pages now. So we need to be very sure about these things. So there are some challenges, but and there are some fiddly things to sort out. But I think in theory, we could get to a stage where Vfio is reliably notified through MMU notifiers and can keep its page tables in sync with the user space page tables. So once notified, what would Vfio do? Well, I'm suggesting a new Iommu domain ops callback, remap PTE, and Vfio could invoke this remap PTE callback, and the Iommu driver would then walk the user space page tables and update the relevant entries in the, walk the Iommu page tables and update the relevant entry in the Iommu page table through this callback. And with that, the page tables are in sync. So there are some challenges here around page table page table entry size changes, specifically things like THP coalescing or splitting while you've got DMA transactions and the line starts to get quite hairy. Maybe you could solve that. Maybe it's limited to say we don't support things like THP and dynamic memory oversubscribed assigned regions. Yes. So okay. So that's the first part of this, which is around unpicking the device and page table. The second part is around the interface to ensure we never have any faults. But let me just take a break here just to solicit some feedback on this first part.
I'm making a really loud hum.
Mm-hmm. I hear the hum too.
I think that one. Okay. Can you hear me? Yes. Okay. So, I mean, we have a lot of experience with what you've just described. We've done it in RDMA for a long time. What you describe as HMM, right? When you say MMU notifiers, you kind of mean the HMM piece of it. The reason it's never worked for the IOMMU is that you can't make it coherent, right? The way the IOMMU notifiers work, they really are intended to be used with the invalidate start end, which means you stop touching it, the MM goes and does something, like maybe it swaps it, maybe it copies it, you know, it does something where it assumes the memory isn't changing anymore, and then you get your invalidate kind of end, and then you get the possibility to put it back in your device. So if you can't pause the device, you fundamentally can't use these techniques. And the IOMMU doesn't give you any way to pause the device unless you have PRI.
Not clear to me why you need to pause the device, because if your contract is that, and this is maybe the next part where we ensure that you never attempt to DMA to a non-resident page, but if your contract is that page will always be faulted in on the CPU side before you attempt a DMA transaction, then so long as that IOMMU page table entry is materialized at the same time as the CPU page table entry, I'm not seeing the need for the pausing.
Well, you don't. Well, no.
Is bidirectional.
Well, if you're doing that, you don't need MMU notifiers. You don't need HMM. What you're implementing is VIOMMU, where the guest tells you to map, and then you map, and then guest tells you to unmap, and you unmap. So you have a defined time period. So you don't need MMU notifiers to implement that at all. We implement that today. It's just really slow.
Right. So if you have that synchronous call, and again, we're maybe getting into the second part here a bit, but if the guest is actually doing hypercalls or something like that to say, I am going to map this page, you're right, then you can hook that into VFO directly. But I'm trying to suggest a more lightweight approach that actually the guest typically doesn't need to do any VM exits, any calls into the hypervisor. It's so long as the page is resident on the CPU side before it initiates the DMA transaction.
So how do you make it resident on the CPU side without a hypercall?
Yeah, that is the second part.
That's the next part. Okay. Then.
Just one moment.
Sure.
Can you hear me in the room?
It was basically the same thing. It strikes me that you don't have a good guarantee so far. You'll explain that you'll fault in on the CPU first, and without that, no MMU notifiers. And I mean,
cool.
I'm with Jason on that because the normal paradigm, normal for whatever the definition of normal, is that you would use the virtual IOMMU structure. Hypervisor, hey, go and map this. Whatever definition of that.
I think you're right. Maybe there's another one to say. Okay, so basically we have where the MMU notifiers are hooked in, and when CPU page table entries are materialized, we'll also materialize page table entries on the IOMMU page tables. So how do we now ensure that a DMA transaction is never initiated to a unmapped page? Again, there's a prior art here around ATS and PRI, but we are looking for a more generic solution that doesn't require these hardware techniques. As mentioned, we can indeed use VIO MMUs, but these would be expensive, potentially requiring VM exits and notifications on every unmapping and remapping. So I'm trying to look for a more lightweight solution here. And the suggestion is basically ensure that the guest kernel does a CPU access to the page before considering it DMA-able. So to ensure that it's resident, basically. If the page is already resident, then this is just a simple CPU access. If the page is not yet resident, perhaps it's lazy allocation, perhaps it's been swapped out, then the CPU access will trigger a page fault. You'll trap into KVM, MM will allocate the page, and via the MMU notifiers, it will then update the IOMMU page tables as well. So as part of that CPU access, you ensure that the page table is resident both in CPU and in IOMMU page tables. And just a simple CPU access is good enough if you're only doing lazy allocation. If you want to be able to support host-side swap as well, then you could do this with a shared bitmap, where the guest kernel would set a bit in this bitmap when it maps the page for DMA, and the host would then need to consult this bitmap before attempting a swap out operation. And if the bit is set, it knows, like, I'm not allowed to swap this out. The guest could potentially be using it for DMA. Some careful coordination is needed here to avoid races. So on the host side, you would first zap the CPU page table entry, then consult the bitmap, and only if it's clear, then zap the IOMMU page table and return the page. And that's why I mentioned at the start, we may not want to use SVA and actually keep them strictly in sync, because we would want to sequence these teardown operations quite carefully to ensure there are no race conditions. There are a few in the guest. We could expose it as an IOMMU. It's not really an IOMMU. I think it's the wrong abstraction. We could attempt to hook into DMA map ops. Again, we would end up doing something that looks and feels quite a lot like an IOMMU, needing to implement a whole bunch of callbacks. My suggestion is actually to hook into the DMA direct functions. So this does not have an IOMMU. As part of mapping and unmapping pages for DMA, it just goes through these DMA direct functions. And inside there, we could invoke the callbacks to this device driver, which would be responsible for doing the CPU access to ensure it's resident and doing the bitmap maintenance. So we have a few options here. The last aspect is around how this page pinning device should be exposed by the host and discovered by the guest. It's a pretty lightweight device. Essentially, it just needs to be discovered so that the guest knows, okay, I need to do this. I need to register these callbacks and do the CPU access as part of the DMA mapping sequence. And perhaps a few registers as well, so that the guest can share this bitmap with the host. But it's a really lightweight device. The important thing is it needs to be set up really early before any DMA operations are performed, so that the hooks can be installed. Again, a few options here. We could piggyback on an existing device like VirtIO, or we could add a new device to ACPI. I don't really know what the best approach for exposing would be. Cool. So in summary, we've looked at two aspects of this problem. The one is getting the guest this lightweight protocol where the guest typically doesn't encounter a VM exit, but ensures that the pages are resident before initiating a DMA operation. And also, I have another to the guest QMU with this functionality and with doing a subscription with PCIe classes. Did need to sprinkle some more MMU notifiers to get it to it. The next steps would be to announce relations to IOMMU. That's a lot of overlap how you were speaking about IOMMU talk. And yeah, if people are keen on this approach, next would be to send out an RFC for making Vfio dynamic and start the discussion on how to expose the device model. Thank you.
Just have a quick question. You mentioned that touching a page is lightweight compared to hypercore on the architecture I care about. That's not the case. I mean, it's exactly the same cost. I mean, you basically take a full exit all the way into the rest of the kernel to perform the gov.
To access a page.
Yeah, if it's not mapped. If it's not mapped.
When it's mapped, you don't take it.
No, of course not.
And that's the 99.999% case.
Yeah.
But if you want that page, you have two things. You access the page to guarantee that you will be able to map it in your Iommu. You have to do that whatever you do, but you need to perform that mapping once. So why do you bother having this infrastructure, whilst you could have done a hypercore that has the same cost as the initial mapping and pin the page in the first place?
So pages get mapped and unmapped quite often, right? If you're doing, for example, if you're allocating pages for page cache to DMA block devices into, you're mapping and unmapping pages all over the address space. And you don't want to turn every single one of those map and unmaps into VM exits and hypercalls. The best thing would be if the first access to one of those pages encounters a page fault, and then from then on, you're basically just setting and clearing this bit as you unmap it, because it's now a resident page. So only the first access that actually makes it resident requires a VM exit. From then, you can map and unmap in a very lightweight manner without any VM exits. If you expose a virtual Iommu, every time you do that mapping and unmapping, you need a VM exit and some flushing probably as well. And that's the whole thing. We're trying to optimize for this case of not doing VM exits in the general case. Only do it when you really have to, when you really need to fault that page in because it's not resident.
So you have basically a lightweight page lock. So you effectively have a lightweight page lock.
Right.
Well, it has nothing to do with mappings. It has to do with locking the page.
Exactly, but it's locking hooked into the DMA mapping functions, because those are already invoked by a device driver when it makes it page DMAable. So that's why it's a really useful place to hook in. Super simple to hook in there, I think. You want a box? Here we go.
If somebody else wants to speak, please go ahead. But it strikes me that this box does not like me. I'm too close to the other boxes, to the speakers. Okay. It strikes me that it's exactly what you said. You've created a lightweight. Okay. Let's try again. Then you created a lightweight way. Yeah, I did that. I thought that's what made it worse. Oh gosh, a lightweight way to lock a page, right? And to me, that kind of suggests that what you've created here is part of the KVM layer in a sense, and maybe less part of the Iommu side. Because I am thinking about your question here. How do we model this thing? And in a very real way, it's the KVM, like connect a KVM page table to an Iommu domain that mechanism specifically to avoid the PRI requirement. And that might give you some guidance on how the modeling can work for you.
So yeah, just one comment there. I didn't necessarily want to make it KVM specific. I don't see a reason why you couldn't use a similar approach for DPDK, although my focus has been on the virtualization case. Yeah.
Because it makes the modeling easier is kind of my answer. Yeah. Like we already want to connect KVM, and especially if you could do the SVA, like where you could actually share the KVM page table. Like if you could figure out the way to make the locking work where that could be possible, like that would be really, really appealing to say that we could share the KVM page table. KVM takes care of all the MMU notifier stuff because it already knows how. And all you're adding is basically page locking on top of that somehow, lightweight page locking. That I think that would be really appealing because the KVM page table today. in a lot of architectures. But we don't have a solution to
What I'm still trying to, it sounds like you're suggesting that we still pursue the page table sharing in this case. And my point, I think that unless you actually have PRI, proper page table sharing is not desirable, because especially on the teardown sequence, when you want to stagger the sequence. You first want to zap it on the CPU page table, then consult your locking bitmap, and then tear it down. And I think for that reason, you actually don't want the real page table sharing unless you have proper PRI.
Yeah, that's why I kind of left it open. If you could figure out a way to do the locking without that, then that would be great.
Yeah.
I'm just reluctant to duplicate all that MME notifier code. It's
What's the duplication? What are you concerned about?
is already maintaining the
And fundamentally, we are relying on the guests to be well behaved. That's why I've kind of put the title cooperative here. So we expect them not to be malicious and go and like pin all their memory at once. But you're right that is probably a problem that, you know, what do you do in that case? And I guess your options are you can terminate a VM or attempt to detect this early and live migrate before your memory. They all want to pin all their memory all the time. I'm not sure there is a good way out of that. Yeah, don't have a solid answer to that.
You could extend the protocol a bit and implement some kind of a pinning quota for each VM.
That sounds super complicated. The question is basically the same as, what if my oversubscribed user space application that has like an mmap of 10 gig, what if it touches every page in a busy loop, right? It could. And just kills you. And the same thing applies to non-device assigned VMs that are overcommitted. What if my VM goes and basically just has one thread looping through every 4K page of that guest and touching every single one? Well, tough luck, right? That there's nothing you can do except throttling it or killing it. And this is exactly the same answer.
You would be the kill victim then if you're doing that.
It's not a device-specific problem, is what I'm saying. It's a bigger artifact.
It's not sure that you get killed when you do this. It could also be that someone else gets killed. So,
correct.
Right, and then you have a victim who did nothing wrong, and the bad behavior continues.
Again, I'm failing to understand the difference between a CPU-based page touching mechanism and the device-based page touch mechanism. It's the same problem. So I don't think we need to build anything special for device-based pinning, because it's exactly the same set of rules you want to apply.
And also, this would be like a pretty unusual case that you would detect, right? If that bitmap really is all set, there's something wrong with that guest, because that is not a typical way of doing DMA, right? Typically, you'll scatter DMA across your address space, but things will only be mapped for a shortish interval as page cache pages are allocated.
Depends on your workload.
You want a mic?
Sure. Like
we know of workloads where 90% of the RAM is pinned permanently. Right? Database workloads,
Right.
Specialty workloads, HPC workloads. It depends on your workload. You're talking about a very special workload for you when you say that.
Well, I'm actually trying to solve the general case, and I agree that there will be classes of workloads which are very DMA heavy and will pin a lot of their memory, and those would not be a good candidate for a memory oversubscribed environment, actually. I'm looking for the more general case here, your typical, whatever a typical workload is, but something that is not accessing DMA all the time to its whole address space.
What DMA devices do you imagine installing in the device, in the guest?
Block device and network device. Not accelerators, no. Yeah, typically again, accelerators and those are your high performance workloads, and you typically wouldn't be running them in an oversubscribed environment. Yeah.
Just trying to understand, how do you tell the difference between a guest access that is just a random memory read from an application versus a guest access that's meant to pin some memory?
Sure. I'm not trying to actually tell the difference between those. Basically, what I'm saying is by keeping the Iommu page tables in sync with the CPU page tables through notifiers, so long as something has been faulted in on the CPU side, it will also be DMA-able. And you keep those in sync, and it's only on the swap out path that you need to then go and look at this locking or pinning bitmap and decide, am I allowed to swap this out or not? It will be very rare that you have a cold page. I mean, yeah, that is also DMA. You know, typically if your page is mapped for DMA, it's kind of a hot page. It's being accessed by the CPU. But that's the locking. Again, I don't want to say typically, but that's the locking mechanism. Yeah. So you keep them in sync, consult the bitmap on the swap out or tear down path. That's my time. Thanks very much.
Okay, thanks. So the next session is a virtual one. I think we have to do a short setup and then we continue.
This is different. So it may be. How long is this break?
Oh, look, you can hear me.
Yeah.
Bonus. Right.
You can just bring your volume down to like just the lowest level. Let me see.
My
Your level on here, you could just bring it down to just the lowest
my
level.
microphone level.
Yeah.
I can definitely hear you, David, remotely. I'm not sure if the room can hear you still.
So even if it's like a receiver, you'll go through DMA, and then you'll do this process.
It's amazing. And then the reception
as long as access log says and DMA map you're doing is an issue here now. For example,
so that's back to normal. 1, 2, 3. Yeah, is that right?
Okay. All these oversubscription things are not going to work on this type of devices. So because this is almost first line of your device installation DMA map. So DMA map 10 gigs. You pin from the beginning with 10 gigs, and that's all.
So if you've got that sort of workload,
it's not workload. I'm trying to say it's how Nick operates. It's how Nick.
I don't know because that big. They don't come along and 10 gigs.
Not that
I expect some megabytes. And those megabytes.
Not when you are working with devices, something will get like 25 gigabit more, approaching 1 gigabit, because you need to hold large ring buffers. It's going to be, it's not megabytes. For example, our device,
yeah. So and then yeah, and if that's the case, it's all devices there is no way to make right? So that memory can't be memory oversubscribed. So what we can look at is the memory which is not being used by the device, or is sitting unallocated on the guest, and that's the memory which you're able to access. So I'm not trying to find a way to oversubscribe memory, which is used or can be used as DMA. You definitely, you can tune those buttons. If you make them too big,
something in
you're removing your memory.
something in pressure you are talking about probably.
If this now works.
Yeah, and what we're hearing that loop is
when you want to go to have some limits, some network speed, you need to reduce this page fault or page fault cache. You need to reduce all unknown instructions. This is why you can see the network like that. Network stack is working to introduce your own page allocators just because of it. Because traditional page allocators are not fast discovered.
Yeah. And I think if you're trying to do this very hard, you're right, that's not some games. I think this is very for the case where it's very practical.
Let's say for real devices, it's something close. It didn't sound right.
Specifically the EC2
that's irrelevant.
counters Mc that we use, which is called
EFA
is a more high throughput performance. DNA is just more generic. Users for
I imagine remote builders,
which devices would show next to
Again, it's not only it's part of the problem because you can the problem when you need to share your memory, host memory with firmware, because your firmware on the device needs more memory than the existing device. So this is how it's achieved. You make this memory, give it bidirectional, and so on. This is how firmware NIC device extending his own memory. And it goes without any CPU intervention. Only the main map and CPU information. After that, all the successes.
But you only need that DNA map unmapped. And in that window,
it's okay. I just what I didn't get and still don't get. What is oversubscription? Oversubscription in my speech. Do not wait for page fault to come, and once it's page fault, bring specific memory, and this is oversubscription. Classic oversubscription.
So, but this is slightly different. We're taking that fault earlier when you're networking. So the only memory that we're able to describe is the memory which is not accessible by the device, which is not being used for DMA. So we have a smaller window for this, but it's better than today, right? Today you've got no oversubscription when you're doing PCI devices.
We've done it
because Vfio comes along and your whole so we have no oversubscription. So I'm trying to say, let's do what we can, even if we don't.
How to get with duct tape and deer, you have to set the system up.
So
that program,
Get what opportunity we can. It won't be every day.
I always need to remind you what you're talking about Vfio case. It's like all in my I think only in host hypervisor view.
Okay. I need to grab a copy. Copy before the next one.
Oh, yeah, sure.
Sorry.
Thank you so much. I appreciate it. They don't want them to be shut down. We've helped with the service on foreign aid, you could shut down all payments. But they haven't kind of graduated the requirements.
An email from James.
Yeah, he gave me like, there is a legal effect of.
There was an email with
I should do that password.
Yeah, well, that's
How do you think, chat with
my email had one for EDB and one for matrix chat only.
Okay. Just a second. Okay.
But that's expensive, right? Because building a region starts with land 100 racks of sort of floated technical debt, and then start running customer workload after, right? So that's been a long-running program as well.
So many
models programs. So we depend on that too. Well, okay, maybe not. Maybe what can we do about building a sort of a private local zone or something?
I mean, these.
Yeah,
That's not good enough. It'll
Okay,
still be
so
held, we
this-
control.
events, right?
So then you have autonomy there, so that
Drop from the
it can meet their requirements, and it's.
So I'm uploading my slides to the NBC website. Will you upload them here as well?
Yes.
The is.
So that you can show
Well,
it
our post is still-
Okay.
here on
Our post is still
because
fun.
you can't do wireless.
Control.
That's the thing.
On the copy.
Because we're driving the in-room
We have nothing that can make.
problem.
Okay, so I have time.
It does. I have to actually hear about it.
I also that we were
Yes.
Well, there's no effort, which is that, it's basically just
No,
the whole set of services. Yeah, and then we have to find a sweet spot. What's the
Yeah, I was in the
Hey, well,
yesterday.
in this environment.
Today.
You don't want to press.
On our phone here, because every time you cancel to me.
Or you can send
Okay, then we're
great. Have your simple hats and minimal.
Okay.
But minimal is not, right? I have been, a stone in a lot of room. But the functionality, while not like this here, certainly needs to be more than that. Yeah, so yeah, we don't want to be too functional because it will set too much.
Then you get it as a PVB room.
We don't want to be completely non-functional either. So building up from that, those it's too far.
It should need to be presenter.
Yeah, so we're looking at, can we try to build the autonomy into a set of local zones, which is something else that's already been tested.
Yeah, I think now you can upload.
It's not possible. So yeah, I'm herding cats and trying to find, so which of these impossible answers is least impossible? Meanwhile, I'm getting people whining that I'm being too prescriptive about them. I'm really not. I'll be prescriptive about the requirements, but.
When there is business, into kind of be prescriptive.
Yeah, and everybody says, not in my backyard. Oh yeah, go and make that other team do it that way, and yeah, okay. And that's reasonable, right? Right. That's natural. Good. But no, it's all need to work out if you have.
Yeah.
Work out which is least insane.
Like release. The present is contingent.
I know, although it's hard to predict the actual usage, right? And what revenue do we get? And I think it's even harder.
It's very simple. Because if you win,
we couldn't justify it because for building the region that has its own cost. We couldn't justify it. We're factors of
the other person should take it.
or 20 away from.
No, I just gave them a lecture.
But the revenue prediction, you have no idea, right? And it's just.
Yeah, that's
Plus, given, the big worldwide company and so forth can't use us in France, then why would they continue to use us in other parts of the world? So if they're all away from Europe and I don't know how much that was factored into the potential lost revenue if we got right.
Yeah. But then I was going to try to know why we're recommending it hard, right? But when you actually add up the dollars, and have somebody try and predict that, that's not right. But there are people who do, especially revenue prediction and all that stuff.
Hopefully we can hear them.
Yeah.
From these audio issues.
Purely on the I hope so. There's other reasons why we need to do it, right? But I find myself
Get together and make it.
and those have and we had one last week. And I was picked up on my body language. My body language when I was talking about this goal by the end of September.
Sorry?
Ah,
really? From the
body language.
So I got an email about buses and
Oh yeah, I don't. Yeah, there is
that's a
like
learning
inner
experience. I set my camera on next time.
application.
I said, no, absolutely. Absolutely, and then I was picking on for that because wait, you didn't say you will get it done. You said what do you mean? You don't tell the truth.
Actually, it's a shame.
It's a learning. The way to do that, that's very about you to say we when you divide goal and go down like body
yeah.
There are times when I end up sitting under my desk rocking backwards and forwards. But on the whole, the data. Yes, it depends on the whole
Next gen.
So we can. My job to activate.
It's like an income.
Yeah, it is.
Well, live migration.
Run at faster pace. Exactly. Run at faster pace.
Let me ask them whether the audio works. We can start.
Yeah. Yes, it should be working. We got some feedback from me because I'm physically in the room and my mic is picking up and speaks, of course. But yeah, it should be working.
Then we can follow the next step.
Yes.
Welcome back to the Vfio Iommu PCI micro conference at Plumbers. We now start our next session about PCIe endpoint subsystem open items discussion. I hope the audio works. Manivanan, you can go ahead.
Test. Can you hear me?
Yes, works. Great.
Thanks. Hello, everyone. Okay, let's get started. So welcome to the session on PCI endpoint subsystem open items discussion. So myself, Manivanan Sadasivam, I work as a senior kernel engineer at the Qualcomm landing team of Linaro. And there's also Kishon. Kishon works for TI, and we are both going to discuss a couple of topics that's for improving the PCI endpoint framework in Linux kernel. So the topic that I'm going to talk about is revoking the PCI endpoint notification and device integration. So the first one is revoking the existing PCI endpoint notification. So currently the PCI endpoint framework uses atomic notifiers for passing the events from endpoint controller to endpoint function driver. So the endpoint controller driver is nothing but the device driver for the actual PCI controller. And the endpoint function driver is the driver that constitutes the actual function of the endpoint device. So let's say if you have the modem PCI device, then the endpoint function driver is the one doing the actual data transfer of the modem packets from the endpoint to the host, and then it handles all the connections with the PCI host as well. So the endpoint controller and then the endpoint function needs to talk to each other, pass some events, and for that, the endpoint framework currently uses the atomic notifier mechanism. And there are a couple of events supported. First one is core init, that's used for signaling the complete initialization of the endpoint controller. And the second one is link up, and that's the standard PCI link up event. So the use of atomic notifiers suffers from several issues currently. So the first one is the endpoint function notification or the EPF notification function should be in the atomic context. So even though the endpoint controller that's invoking the atomic notifier may not be in the atomic context, the EPF drivers needs to be in the atomic context for carrying out the notification. So this is adding an overhead to the EPF drivers, because there's no need for the actual atomic context in this case. And that means the EPF notification function cannot use any functions that can potentially sleep. And the present EPF drivers available in mainline, the endpoint test function, is actually one of those, and it is suffering from the sleeping in atomic bug, because it tries to call the EPC functions, and that were using mutex, and so that triggers the sleeping in atomic bug, and this is something not we want. And the second issue is that the notifiers are not a really good candidate for passing the events if there is a concrete fixed interface between the sender and receiver. So this is something Rob Ehring pointed out while reviewing one of the endpoint framework patches. So I would like to address both of these issues with my proposal. So the proposal has already been submitted to the mailing list and being reviewed. So it uses a simple callback mechanism for passing the events from EPC to EPF. So the EPC core will expose the event ops structure. And this structure has a couple of function pointers. One is core init and another one is link up. So these are essentially for the notification events that were in the atomic notifier. So the endpoint function drivers should just really pass relevant functions to these callbacks. And on the occurrence of the event, the EPC core will just execute these callbacks for each of the EPF drivers associated with the EPC. Because for each EPC, there can be multiple EPF drivers, right? Because the endpoint function device can, it is a multifunction device, right? So it can expose multiple endpoint functions. So for each function driver, the endpoint core, EPC core will just go over the list of callbacks. And if the callbacks is populated, it will just call it. So it's pretty simple, it works, and it really gets rid of the overhead associated with the atomic notifier. And it also preserves the context between the EPC and EPF. So if the EPC driver that's invoking the callback is in a non-atomic context, then the EPF atomic and the EPF function can also be in the same context. So the context is completely preserved. So this is one proposal, and then the second issue is device integration.
So, Manivan, have like one question. So, so here for the callbacks itself, you are using mutex logs, right? So that could possibly be events which has to be invoked in an interrupt context. For instance, the link up is usually an interrupt that is raised by the controller. So in general, when it was actually introduced to just have this notifier, so it is up to the function drivers to kind of like decide whether it has to schedule a work and do it as part of a process context, or it has to do it in the interrupt context itself.
So the problem with scheduling I mean, using another scheduler inside the EPF driver is that that introduces latency. So for instance, there is a, let's say there is a core init event, and then we'll have the link up event afterwards. And if we are scheduling one more, the one more function or one more mechanism inside the EPF driver, means that's adding, again, it's introducing some other overhead that we could avoid with this thing. And regarding your mutex, you are right that we cannot use interrupt, or the EPC func caller cannot be in interrupt context, but none of the EPC controller drivers are actually invoking these callbacks in the interrupt context right now. So if you go look into the upstream drivers, only Tegra and then Qualcomm PCIe controllers are invoking these callbacks, and both are using the threaded IRQ for this thing. So mutex just works. And I think most of the controller drivers need not issue these callbacks in the interrupt handler, right? So then we do not know how long the endpoint function is going to take, and that's really not something we really want to do in the IRQ handler, right? So
So here we have like a couple of handlers now, but this is going to extend as we implement more endpoint functionalities. Could be like function level reset. There are like it's just we are just just on the tip of the iceberg, right? There is still a lot of features that could be implemented. So if we start with this approach, then we really don't get into an option of both. So it means the function drivers will never can never be in like an interrupt context itself.
that's what I mean, that's what I said, right? So if you are invoking these callbacks from the EPC driver, then you will not know how much time the EPF driver is going to take, right? So we do not want to block the IRQ handler for a long period of time. So I don't see actually a reason or a point in making the EPF callbacks atomic. So I got the point that the notification has to happen very quickly, so we do not want to add any latency. So in that context, the previous use of atomic notifiers made sense. But still, if you use this simple callback mechanism, that can be actually achieved, and it's really more efficient instead of going through a separate framework, right?
Okay.
Yeah, and there are other notification. The notifications that I'm going to propose, at least for link down and BME events. And I have the endpoint function driver for the MHI use case that I'm going to talk later. And that uses both of these events. So we have at least 4 events working in our downstream driver right now. And that's just works fine. So okay, so the next topic is device tree integration. So currently the device tree is well integrated with the EPC drivers, because most of the EPC or the endpoint controllers are defined in the device tree, like any traditional PCIe controller IP. And that works well. The EPC drivers can make use of the platform data, and then they can extract all the informations like register, IRQ from the device tree. But currently, there is no device integration for endpoint function drivers, just because most of the endpoint function drivers we have seen so far is actually a software implementation. So since device tree is supposed to define only the hardware interfaces, it's not really better. It doesn't made sense so far to use device tree for EPF, but we have started seeing some of the functions, endpoint functions, like in this case MHI. MHI stands for modem host interface. So that's the Qualcomm specific protocol for transferring the data packets most probably the modem or Wi-Fi packets from PCI endpoint to host. And for this endpoint function, that is really a hardware block inside the SoC. So in those cases, it has a specific register region that is usually exposed as a bar to the PCI host. And then we have the interrupts for this block as well. So if we don't have the device tree integration, then currently we are, in the downstream implementation, we are reusing the PCI endpoint controller device tree node for, getting all the platform specific data like bar region, interrupts, etc. But to represent this APF driver in a proper way, I would like to propose a minimal device tree integration for at least for this specific endpoint function driver. We cannot make it as a generic device tree integration because, as I said, most of the endpoint functions are really software implementation, just like how we have the USB gadget. So just for this specific use case, I would like to have the device tree node defined. So the proposal I'm have is that a child node, so a child node for the MHI under the actual EPC node. So this is the PCI endpoint controller IP, and it's the MHI node is actually a child node of this EPC, and then we have the rich property. So since we can have multiple endpoint functions inside the endpoint, so we need to have this register and then the unit address, and then we have the function name. So this actually going to bind with the EPF driver and the bar regions. So we can have multiple bars. So this is actually a tuple, and we can have interrupts. So this interrupts corresponds to the MHI block inside the SoC. So not only using this device integration allows the EPF driver to extract the platform-specific data, it also avoids the overhead of using the config.fs interface for the linking EPC and EPF, and then starting the controller, etc. So currently, since there is no device tree integration, the actual configuration of the endpoint framework happens through config.fs, and but for config.fs, we need to have the user space up and running. And if you are deploying, let's say this MHI in a real product, then we want the product to start as soon as possible, right? During the kernel boot itself. And if you want to wait till the user space start, then that adds some sort of latency, and that's not really user wants. And in this case, since you are going to have the device integration anyway, we can have a steady link between the EPC and EPF because of this parent-child hierarchy, and then that really helps in configuring the or setting up the link between EPC and EPF without the config.fs intervention. And so these are the two advantages of using device integration for MHI function. That's it.
So this one is still in work in progress, correct? You don't have.
Yes, I don't.
Okay.
I haven't proposed anything so far.
Okay.
In the form of patch series.
Okay. So sometime back, actually, when I had added non-transparent bridge function using the PCI endpoint framework, so I had used slightly different binding. So here the PCI EP will be the platform bus, will come under the platform bus, and your func is actually a child of that. But at least for my use case, that wasn't sufficient because it has to deal with two different endpoint controllers. So kind of defined a separate EPF bus on which I had added all these functions. So the difference is actually, so instead of having child to the parent endpoint controller, kind of had a p handle to the endpoint controller. So that way I was able to kind of give a reference to multiple endpoint controllers for a single function.
Yep. So in this case, we don't really need.
We have a question in the room.
Oh, sorry. Yeah.
Hey, Manivan, maybe you can finish answering Kishan's and then I'll kind of come at it. I had a similar question on what the parent-child relationship is going to be between the function and the actual device. So, for example, your modem device is going to be sitting on the PCI bus that's going to get auto-detected. How are you going to tie the controller, the modem, and the function together in hierarchy?
Sure. Yeah, I'll just answer Kishon and then get back to you. Yep. So I did look into your previous proposal for the NTBs, and like you said, you need to have, your function needs to address at least 2 endpoint controllers, right? So in this case, we don't don't actually have a need for that, and at least I envision we might end up having one more function, but that's entirely possible with this model. And then you have used the a specific platform bus for instantiating this device, but in that case, that cannot be really represented in a device tree, right? Because that's really a software layer that cannot be represented in device tree. So what I did was, since the PCIe endpoint is actually a physical IP, and then that thing is going to instantiate these devices or create these EPF devices. So whenever I don't have the proposal right now, but what I envision is that this EPC controller driver is going to create these EPF devices, and so for whatever child node defined in the device tree. So it will just go through the list of child nodes defined in the EPC node, defined under the EPC node, and then it will just go and start creating functions for each of the nodes, right? So and then later on, when the actual EPF driver shows up, it's going to bind together with this guy, and then they are both going to flew together. But the only question I have in mind is that when do we actually need to start the controller? So that thing I haven't really settled on. Either once we bind both EPF device and then the EPF driver, can we start the endpoint controller? Or if you have some other idea in mind, that would be good too.
Yeah, so especially in your case where you don't have, I mean, you are like binding all the functions as part of device tree itself. Then as part of creating a function devices, once you have like created function devices and invoked like the probe of that function drivers, then you could actually start. Unlike so if you confine your case to where you kind of like represent all the function devices in the device tree itself, I don't think that's not an issue. The only issue is if you kind of like have some things represented in device tree and some things you have to like in a more flexible endpoint controller, which actually lets you do all that. So only in that case, so the only constraint is you have to start the endpoint controller only after like all your endpoint function devices have been like configured. So or else the host would see some undesired results.
Yeah.
So as long as you confine your problem to just that, I think it's possible for you to just start the endpoint controller as soon as you kind of like probed all your function devices.
Okay.
Itself.
Okay. Okay. Thanks. Can I get back to the other question?
Yeah, sure.
Okay, can you please reiterate that? I cannot understand.
Okay. Looks like my mic is working. Just to restate my question. By the way, I'm nowhere close to a PC expert, so please correct me if I'm wrong, completely wrong. But in terms of my understanding, the modem is going to be a PCI device that's kind of scanned by the controller and populated. And you're saying this function is going to be a function of that modem in this example. So shouldn't this really be if this was like a child of the modem? And if so, how are you going to tie this function to that particular PCI device? Like, how do you know that this is given by the sort of some other random device in the PCI bus?
Yeah. But this is actually a representation of the actual endpoint device. There's no host in here. So this is the device tree node or entire device tree for the endpoint device, right? So this is how we represent the endpoint device inside the endpoint. So there's nothing host specific here. So once this is completely tied, then this whole thing is going to show up to the host as a actual PCI device. So you cannot really separate these two things
PCI
together.
device. Sorry, go on.
Yeah. So this function is what making up the whole PCI endpoint device, right? So these whole things are just represented as a single PCI device with a defined VAD PID to the host.
Okay. So you're saying there'll be a PCI device that corresponds to this, but I think you also mentioned like an EPF device or EFP device in the slides that'll correspond to this too. There was one the child or
Yeah, so that's the virtual device we are talking about, not the physical device. The EPF device is the internal kernel device created for each of the function, because the actual endpoint framework is actually a bus inside the kernel. So we need to have a device, virtual device, and then we need to have a driver that gets bind to it. So this thing is going to have a virtual device created for it, and then we'll have the actual PCI endpoint function driver that binds to it, and these both will work together to form a complete PCI device.
and like, what would be the parent of that function? What would be the parent of the virtual device? What
So
device would be
that's
the
going to
parent?
be the controller.
Shouldn't it really be the virtual device that corresponds to the modem, or are you saying there's no device for the modem, if I understand correctly? We'll
No,
scan and
there's
you'll
no
introduce.
device for the modem, because the thing you are talking about is completely different. You are talking about from the host perspective. So whenever you are attaching a PCI device to the host, then you'll have a device showing up, and then so that will have a separate in-kernel device, right? That's a different thing. So this thing is only a endpoint representation. I think that's where the
Right,
confusion
but the
lies.
point is, if this endpoint is being supplied by that other device, shouldn't you set up the parent of this endpoint to be that other device?
No, you cannot really do that. So because this is the EPC device, as per the endpoint framework, you
No,
need
I'm
to
looking
have
at
a
the bus
EPC.
versus-
Yeah.
Just to be clear, I'm not mixing up the virtual device and physical device. Fully understand it.
Yeah.
I'm also not mixing up the buses. A device in one bus can be a parent of a device in another bus. The reason I'm talking about the hierarchy and whatnot is my real question comes down to, if you're having multiple devices, PCI devices on the PCI bus, and you're having multiple functions under the controller, how would you tie the function to a particular PCI device? So I'm just making up, right? Let's say other PCI device be like a GPU in the PCI bus.
So probably
They'll all come to the same controller.
So let me try and answer that. So if you see whatever Mani has presented here, right? So the PCI EP here is actually a platform device, right? So when this driver probes, so there are there is like a hierarchy of devices. One is the platform device, which is part of the platform bus. So the driver actually sees this as an endpoint controller. So it will create what is called as the EPC device, which is called the endpoint controller device. And whatever you see below func, right, that is called func device, EPF function device. So all this EPF function device will be connected to the same EPC device. The EPC device itself is coming from a separate platform device, but the hierarchy is like that. So there will be leaf nodes. If you just think, there will be multiple leaf nodes, EPF device, which is all part of this func 0, func 1 based on how many ever functions are there. And the parent of that will be the EPC device, which is created by the endpoint controller framework when someone adds an endpoint controller to the framework. Like for instance, here the driver that corresponds to this Qualcomm will create this EPC device when it registers with the framework.
Okay, so it looks like, at least in this case, you're saying all the child func devices would be marked as the child of the other EPC you're talking about.
Right.
We're looking at the parent-child relationship in DT to figure out what function belongs to which controller.
Yeah. So if you're having a separate GPU device, and then if you are having a separate modem PCI device, then even for a GPU device, there needs to be a PCIe controller in it, right, to talk to the PCI bus, and that will become the parent of the actual function implementing the GPU. So this same setup is
Yeah,
going to get
that's where
replicated on
my
whatever
disconnect
devices.
is.
Yeah.
Yeah, I thought there'd be one controller for a bus, and then you can have multiple PCI devices on the bus, is what I thought was the
Oh,
right
no,
interpretation.
that's
But like,
no.
I could be wrong, so I don't want to digress too much. Thank you.
Yeah, so this is not a root complex controller driver we are talking about. So this is the endpoint
I
controller
think that's what I'm
driver.
thinking.
Yeah,
Okay, thank
yeah.
you.
So Mani, like couple of points. So one is, so here it looks like the MHI here would always be like a function to this endpoint controller, which will be used by the host. But that could also be a case where, any standard platform device could be exported to the remote host as an endpoint device based on, how you configure.
So at least on this Qualcomm's platform or any of the endpoint based Qualcomm platforms, we cannot really use any other functions.
Yeah,
there
I
has to be
understand.
only one function.
Yeah, I understand this part, but a more flexible use case, if you just really think, right, it could be like any, let's say you could have any MMC controller, like for instance, that's present in an SoC. Instead of connecting directly to, instead of presenting it as a device, as a peripheral device for that Linux boot, it could actually bound as an endpoint function device to the endpoint controller, which could then be actually used by the remote host.
Yeah.
So when you actually, so probably we don't have to solve this, but when you actually define the binding, or when you actually think about the solution, probably this is also one of the use cases that you would have to look into.
So, yeah, just going by the use case, I don't see a real need for that, because the present Qualcomm devices all, they have this control PCI endpoint controller, and then they have this MHI, and either that MHI is going to talk to the modem DSP, or it's going to talk to the WLAN coprocessor for getting the modem packets. So these are the only, the at least present use cases that I can see.
Okay, so yeah, I agree from the Qualcomm's point of view, but a more generic use case, not just confining to Qualcomm, but NXPs, TIs everywhere, right? So there is actually, that could actually be a use case where you have to export an actual peripheral controller to the remote device.
Right. So then you are talking about a generic device to integration for the function drivers, right?
Right.
Okay, that makes sense. Yeah, I'll think about it. Yeah.
That seems like a key use case to me. And also, in your example here, are you duplicating the addresses and interrupts that the MHI has?
It's not really a duplication. It's not present in the endpoint controller node.
No, like, is interrupt 440 the interrupt that the MHI node would have?
Sorry, I don't really get how the duplication comes in.
Well, let me ask another way. Is there an MHI node somewhere else in the device tree?
No.
Okay, I think it's time to wrap this discussion up. We are due for the next talk. Maybe we can continue it in the chat. So next speaker is AJ, and he is talking about instant detection of virtual devices. AJ, are you?
Yes, can you hear me?
Yes, we can hear you.
Can you help me to upload the slides?
Oh, I can't make you presenter. Are you already? Yeah, you're already presenter. You can switch to your slides on the. Have you uploaded your slides to PBB?
I'm uploading. Yeah, here.
Yeah, we can see your slides now.
Okay, shall I start?
Yeah, go ahead.
Yep, thanks. Hi all, thanks for joining. Myself, Ajay, works for VMware along with Alexi and Ashwin. Let me start. Yeah. Hi all, thanks for joining. Myself, Ajay, works for VMware along with Alexi and Ashwin. So our talk is on instant detection of virtual devices. And for next couple of minutes, we'll be talking about the detection and initialization of virtual devices within the VM. We will start with the importance of kernel boot time specific to virtual machine and containers, followed by problem statement that is initialization time of the virtual devices. We will explore more here to see which component is taking time to initialize the virtual devices. Then we will move to the solution part. Here we will cover progressive solutions. The one of them is MMIO direct read, followed by skip write, and then we will have one more solution that is a pre-configured PCI config. So all these solutions will be a progressive solutions, one top of another. And at the end, we will finish this talk with some improvements, suggestions, and benchmarking readings. We have VM-based pure and isolated containers. Those are highly optimized to run the Linux kernel. So one of them is from VMware, that is CRX, called as container runtime. And Intel also has that's named as a kata container. So both of have the same properties, like they can bypass the BIOS and launch the Linux kernel directly. So this is to reduce the boot time of VM, and this behaves like a container in respect to the boot time. So it is very critical for CRX and kata containers to boot fast, as much as quick as container. So both CRX and kata container executes Linux application as if they were running in an isolated environment. So we need Linux which boots very quickly. So here Penguin represents the Linux kernel, but here we have a Penguin which is running. So it is representing the Linux kernel which boots very fast. Let's move to the problem statement. So during kernel boot, a lot of the time consumed to detect and initialize the virtual devices, as pointed here by red line. All readings within this tag, within our talk, those are based on the VMware hypervisor. So CRX took less than 100 millisecond to boot. And from this 100 millisecond, approximate 52 millisecond have been taken to detect and initialize the virtual devices, and which is more than half of the CRX boot time. So we would like to reduce this virtual device detection and initialization time as much as possible. As we can see in this diagram, so CRX is mainly booting within 100 millisecond, which includes most of the time from the kernel boot time. And within this kernel boot time, 52 milliseconds have been taken to just detect and initialize the PCI devices. So our goal is to reduce the initialization time of the virtual devices as much as possible. Let's see why read or write operation takes so much time. So each PCI config read-write operation took approximately 10 microseconds. This is because guest will call VM exit to perform the PCI config read-write operation. Context switch will happen from the guest to the host, and host will perform the read and write within your PCI config space. These spaces may be in form of pages or may be in form of structure depending upon the hypervisors. then calls VM resume to return the execution back to the guest. So here we can see the red lines. So from the guest, we have called PCI config rewrite operation, which eventually call VM exit. And then we need to perform the context switch uh, to basically switch the execution context from guest to the hypervisor. Now the hypervisor will perform the read write operation with the config space or structure or pages, and whatever the value in case of write, we will modify the value, and in case of read, we will return the value. And again, the same way, we will call the VM resume, and the execution flow will come back to guest. So whole this single operation will take around 10 microseconds. So So in our case, in our CRX case, with average configuration we have, so we observed like during the boot, we are calling more than 3000, that is 3250 PCI read, PCI config read and write operation we will perform. And if we will calculate, so it will add on approximately 30 millisecond of time. So more than 30. So apart from this 52 millisecond, so most of the time is consumed by PCI read and write operations. So now question is how to improve this thing. So first let's go to the MMIO direct read solution. Here, guest, if we can, I mean, as per the previous slide, so guest was not having direct access to PCI config pages or PCI config structures. So problem will be solved if somehow guest get the direct access to the PCI config pages. This can be easily happen if we will map the PCI config pages or structures, I mean pages which holds the PCI config to the guest MMIO region. Now guest can directly read the PCI config as we can see with the green dotted lines. No need to perform VM exit or VM resume. So no more context switch will happen, and we will save that 10 microseconds. This mapping needs to be done as read only because for the write case, hypervisor hypervisor may need to perform some action apart from just modifying the PCI config. So we have seen in case of write, even if you want to just change the status, so hypervisor needs to take some action at that point. So now next part is while doing this exercise, so we have config, which is of 256 MB. But we may think of like we are mapping completely 256 MB, but no. Here.
Isaac, can you please advance your slide? We're still on slide 6 for you on the previous one. I think on the tool you need to click on. Okay, perfect. Thank you.
Okay, thanks. Okay, let me repeat few things very quickly. So here we are mapping the PCI config space to the guest MMIO region. So as we can see in the green dotted lines. So if we will have the mapping, so we, I mean, no need to call VM exit and context switch and again VM resume. So this mapping is from the hypervisor space to the guest space. So guest can now directly read the MMIO. I mean, from the MMIO region, they can directly read. And next part, I was I was going through the MMIO config. So MMIO config is of 256 MB. But we no need to map or allocate 256 MB. So we need to only map the pages or page per device or bridges within the system. So we are not going to waste complete 256 MB according to our requirement, like according to the number of devices or bridges, we will allocate the pages for to keep the PCI config of particular device or bridge, and that will be mapped. Next side effect. So as we have seen now, guest will perform the read operation, means the control execution control will not reach to the hypervisor. So hypervisor, I mean, if for any read operation, hypervisor is performing any action, so that will be skipped. So to recover this thing or to improve the to make sure there is not side effect. So we have observed some side effects. So those things we have already improved. Means whatever the action we were doing at the read time, so we have performed those actions whenever it was required.
Can you elaborate on those side effects? I'm not quite sure what are you talking about side effects of the PCI config read or something
Yes.
else?
PCI config read. So as we are performing direct read, so hypervisor is not having having the execution control while performing the read operation. Whatever the actions currently we have within the hypervisor, so that action will be skipped. Just take an example for some interrupt cases. You are reading some interrupt values within this PCI configuration space, and that interrupt value is not updated. So in some hypervisor, those will be calculated on the runtime during the read operation. So those things we need to updated within the PCI config space. To benchmark the performance improvement with this MMIO direct read, we written some test application which will call the raw PCI read function 100,000 times for PIO, MMIO, and MMIO direct read. So as we can see here, for PIO to perform 100,000 reads, it took around 12.809 seconds, and same number of operations performed within 8.517 seconds for MMIO case. And any guesses for MMIO direct read case, how much improvement we got? Okay, for MMIO direct read case, so we performed 100,000 reads within 0.01 second. So it's very quick now to perform the read operations. Let's move to the next progressive solution, that is the skip write. So now we have direct read part. So what we are trying to do here is, before performing any write operation, we will read the value, which is very fast. And if same value is already written, we will perform skip write. Means we will not perform the write operation, we will skip the write operation. So by doing this, we got another 12% of improvement. So in the earlier case, we got around more than 60% of the improvement with MMIO direct read. So with skip write, on top of that, we gain 12% improvement. So here, same question for the side effects. So in case of write, hypervisor needs to do some operations. So we need to handle all these cases very carefully. Like, we should not perform any skip write if some action is required from the hypervisor side. So now the third part, that is the pre-initialized. So in pre-initialized part, so now we have read, direct read part, we have skip write part. So on top of that, why not have some pre-initialized or pre-configured? So what we will do in this part, we have PCI config space. So as we can see red lines in here, we will pre-configure the PCI config space by some guessing or whatever we can expect the value should be, so that we will write here from the hypervisor side itself before starting the VM. So at the VM end, what will happen whenever it will try to write something here? So it will first perform the direct read part, and it will skip. If the value is same, our guess value from the hypervisor cell is same, so it will skip this. So as of now, we got around 2% further improvement with pre-initialized approach. And we are expecting that this can be enhanced further to have more improvement from here. Let's see the improvements with all these three approaches. So earlier we were having read-write calls, as in the here we can see. So it's more than 3,000, around 3,200. And after the MMIO direct read, we reduced these calls to around 1,000. And again, on top of MMIO direct read, we have skip write. So again, we improved 12%, and with pre-init, we improved 2%. So now we have near about 300 of these calls are remaining. And in terms of boot time, we got the improvement like 60% with MMIO direct. So boot time is reduced from 52 millisecond to less than 20 second. And with skip write and pre-init, it again reduced further to around 21 to 22 millisecond. So here also we can see the same thing, like MMIO direct did improved around 60 to 65%, and on top of that, skip write provides to improve up to 78%, and pre-init with pre-init we improved up to 80%.
Yes, there you go. Now I'm muted. So can you go into some details? I'm confused on two things. The first is the skip write is something you do in the guest, correct? Because otherwise it just wouldn't make sense. Otherwise you don't save on the exits. So are you patching the
skip write is yes. Skip write is from guest side, right?
Okay. You mentioned that you need to be careful that you don't skip any writes that are important. I don't have all of the PCI config space specs in my head, but are there any bits where you, for example, have a write clear where skip write just wouldn't work systematically for everything?
Yes, true. We have some scenarios where skip write, we should not perform the skip write.
Okay, so how do you generically implement that then? Is there a patch set already I can look at?
Not available. I mean, from guest side, you can specify if this is the particular configuration, then don't perform the skip write.
I would expect that we're looking for some solution that is generically applicable that just works everywhere, right? So we would need to have some.
Right. This is not completely. I mean, this is still we are working, looking for suggestions for these two parts. But MMIO direct read performs very well.
Okay, let's jump to the second question then, because maybe that clears up the first as well. Out of the remaining, and maybe even including the skip writes parts, what writes do you still see that actually are valuable? I would imagine that, especially in a full VM context where you also pre-initialize a bunch of structures and sets, like bus mastering is enabled by default, and your bars are all allocated and so on. What writes do you actually still need on boot at all?
As you said, that's correct. We need to pre-init the bus device and function numbers. That works very well. That gives us performance improvement.
No, the question is, what is still left? You still have 300 exits. It sounds like 300 useless exits. What are these 300 exits that you still see?
Oh, okay. So from 300, there are few read access still left. We haven't done for the root device. There are some problems we are facing for the root device. For root device, we are not performing direct read. And for write part, there are few things which we are not performing for the skip write. I mean, we can go in detail of PCI config. I think we have.
I think that'd be very useful and handy in the conversation. Björn raises his hand. 1 second, Björn. The point I was getting to is since we are talking about a PV feature here anyways, like if the guest is aware that it may or may not want to go and poke at things, and we are providing a thing that looks like PCI Express but isn't actually fully PCI Express as in hardware anyways, maybe it makes sense to really start thinking of telling the guest to skip parts of these pieces of the initialization at all, so that we can save even more on device initialization logic. Like ideally in a PCI Express world with pre-initialized devices, you shouldn't have to have any exits at all just to enumerate what PCI Express topology you have. I cannot think of any reason at all, if you take it to an extreme, why you should need to exit. And I think this is what I hope this is what Björn is getting to as well. But please correct me if I'm wrong, Björn. I would like to move this conversation and this session then towards how can we even get rid of those 300? What problems do you have on the root bridge, for example? What other clears do you have that maybe shouldn't even get emitted at all because you don't need them? You don't need to clear a bit somewhere because it just isn't even set.
Yes.
With that, Björn, there you go. You can lead that conversation because I think there's a big echo if I do that, and so it's going to be easier for you.
Okay.
Oh yeah, thanks. I'm gonna add. I mean, I have basic questions. I'm not sophisticated enough to talk about the guest side. I'm curious about. I understand your chart about your PIO and MMIO. I think you're talking about CF8, CFC versus ECAM, basically there, right?
Yes.
And then I'm confused about what you mean by MMIO direct read. Are there actual PCI Express transactions there in the direct read?
As of now, I will go one by one very quickly. PIO, as you said, CF, those are port-based communications.
Right.
And in case of MMIO virtualization world, it will internally perform VM exit, or you can say page fold, and then land up with the hypervisor, and hypervisor will perform the action and return back. So now in case of MMIO direct read, which is we are proposing, so in that case, we will be mapping the pages which holds the PCI configurations of the devices to the MMIO region of the guest. So that means now guest can directly read. It will perform the MMIO from the guest side. There is no change from the guest side, but now guest will directly able to read the PCI config of the devices or bridges.
Right. So you're avoiding all the VM exits and all that stuff,
Yes,
right?
exactly.
So it sounds like you said the PCI Express transaction still occurs in that case?
Sorry, can you repeat?
I can explain it, Ajay.
Yes, Alexei,
If
please.
you mind. So we are saying about virtual devices, not physical, right? So virtual devices are implemented in our case, it is VMX process. In case of like, or it could be like in Iommu, right? So where execution flow, when it does access to virtual device mconfig space, it needs to do VM exit and then switch context to QEMU to interpret this operation there, I mean to simulate it, and then go back. Basically, we do virtualization overhead. We do not physically speak to PCI device. So it is all virtual devices.
Ah, okay. Yeah.
And in case of MMIO direct read, we just map virtual devices structure, which represents mmconfig, to the guest ECAM region.
Right. Okay. Yeah. Sorry for that distraction.
Mm-hmm. Thank you.
Thanks, Alexei.
And also to answer previous questions, so we really interested to reduce and
Ja? Jörg, ist das dein? Hast du den Button? Oder ist der hinten?
Nee, das ist der gleiche Button.
Ich hatte einen eigenen. You're doing the button? Okay, I see. Sorry, that's a mute button in the back of the room, so we need to coordinate when. It sounds like my questions are basically unsolved still. So I do need to lead that conversation. Sorry. What you're doing is you're trying to accelerate the device enumeration, right? You're basically just saying instead of bouncing back and forth using access into your eCam emulation layer, you just directly map pages into the guest, and then you can just directly read that. For writes, you still need to trap. Fair enough. But the end goal you have is not the technical implementation. The end goal you have is that you want to have device enumeration that is super low cost because you're optimizing for every millisecond there is. And you still have 17 milliseconds. It's an eternity. Right, 17 milliseconds to finish your device enumeration. That really should be something in the order of 1 to 2. So we are still burning too much time in that initialization path. I think the path you're taking there is absolutely correct. But I want to push forward to see if we can avoid even more of any of these operations. And for that, we do need that conversation in this room. Including Björn and where his red line is of where he would be interested and appeal to still modify the core of how Linux PCI works, in just not doing any operations at all. Like basically you want to move the PCI layer to be read-only as much as you can on eCam and not ever write if it can avoid it.
Yes, this is ultimately our goal. So as of now, what we have remaining is we still allow Linux guest to perform the mapping of the PCIe resources. So ideally, it can be performed on the VMX side before even starting the guest, right?
Sorry, say again?
So one of the questions was what we still write to the virtual PCI device. So one example is the mapping of the bars, like register and memory regions. So we still rely on the kernel to perform mapping.
I don't doesn't parse like I don't know. You rely on QEMU too?
Not QEMU. We rely on the guest kernel.
Kernel, okay.
Yes, to perform the mapping of the virtual device resources, like IO regions or memory regions.
Yeah, but they're pre-populated. When you boot your firmware is going to allocate your bars. And
we don't have firmware.
Leave them alone. If you don't have firmware, then your hypervisor plays that role of the firmware, so your hypervisor pre-initializes the bar regions.
Correct. This is our follow-up work, even to map it from the hypervisor side before we even start the guest.
Oh, I see. So you don't do that yet?
Yes, correct. So this is the answer for the question, what is still remaining?
Okay, I see. That's a big one, yes. Okay, so you're basically saying if you did that as well, you could probably get away without doing almost any work today already without modifying Linux at all. Because the reason I'm asking is I've been pondering on this idea for a few years already. I just never got around to implement it. So I don't have any benchmarks or numbers to figure out what else is missing and whether there is anything missing. And what I hear from you is that very likely if you already have bars mapped like you would do in the normal firmware world, and you do a skip, maybe the skipped write or not, but the skipped write sounds like a pretty nasty hack. You can get away with basically no writes. That means we need to find an absolute skipped writes.
Theoretically, yes.
Okay.
In practice, internally in discussion, we split the remaining writes on several groups. So some of them were impossible to eliminate without some metadata. And internally, we suggested to use device tree as the extra information provided by the hypervisor to the guest.
Okay, I'm having a hard time hearing what you're saying, but yeah.
I can try to speak slowly. So I see some echo. I mean, in the audience.
Yeah, the audio setup is not great.
So,
the mic
so,
thing
so,
because that you're speaking through, and so you're hearing yourself.
there are some rights cannot be initialized by the hypervisor before guest start without extra metadata provided to the guest. So basically, direct read is not enough to get everything that we need. So and internally, we suggest to use device tree as the metadata that hypervisor can provide per virtual device.
Okay, what bits are we talking about, and do we actually have to control them?
Oh, Jay, can you so in mind what extra rights do you still have left? We can discuss it here.
Can we? I mean, can we discuss offline? Can you send some? I mean,
let's move them
discuss
out.
over the
Move it
emails.
offline.
Yeah, I think it's a good idea to wrap this discussion up and continue it in the hack room or in the chat or via email.
Sure.
Thanks everyone for the interesting discussion. We now have an 11-minute break, and the next session will be half after the hour.
trying to.
Let's get to the next session from Oded about exposing PCI technologies into virtual machines.
Hi. So, hi everyone. I'm Oded. I'm working at. Oh.
Did you turn it on?
Oh.
There's a switch on the.
Just a second.
We can hear you, but the people online maybe not.
Here? Switch is here. Okay. Right. So, thanks. Okay, so my name is Oded. I'm working at Habana Labs, which is an Intel company. We're developing deep learning accelerators, and I'm the kernel maintainer of the Linux driver. So I'm here to talk to you today about the problem that the kernel today doesn't support doing PCI peer-to-peer inside a virtual machine. So basically, when we want to do peer-to-peer between two PCI devices, the kernel needs to validate that those PCI devices can actually do peer-to-peer. And today, this is done by calling this function inside the kernel, called map type and dist, catchy name, which takes the two peers and runs a series of checks on them to see if those peers can actually talk. And let's see what it does. So here I have.
Sorry, could you full screen the presentation?
Oh, yeah.
While you're doing it, is that possible?
Yeah, just a second.
The three dots on the top, the dot.
Okay.
No dot below. On the publish of his slides. Oh, yes, that's it. Yes.
Thank you.
Okay. So this is an example of a configuration of a server with 8 accelerators and 4 RDMA Rocky NICs that is used for doing deep learning topologies. So we have here the accelerators that does the computation, and then the NICs are used to distribute the results of the computation around the cluster. This is used for something we call the scale out, and the classic example of the flow of data is that the CPU, the accelerator is using its DMA to get data into its device memory. You do some computation on it, and then the NIC takes that data, and then the compute accelerator copies that data back to the memory of the CPU, and then the NIC takes that data from that memory and sends it over the Ethernet. And when doing peer-to-peer, instead of doing this copy back of the results to the memory of the CPU, the NIC directly access the on-device memory of the compute accelerator and reads the data from there and sends it over the Ethernet network. And on the receiving side, the NIC will write the data directly into the memory of the compute accelerator. So this is basically peer-to-peer. And there are a couple of scenarios where peer-to-peer can be done. So this function checks that those scenarios are valid. So for instance, the first thing it wants to check is that if these devices are behind the same PCI switch, then it will check that the PCI switch has its ACS peer-to-peer forwarding disabled. This is a feature that is part of the PCI spec that will cause all peer-to-peer traffic to be forwarded to the root complex. So if they are behind the same switch and that feature is disabled, then that function says, okay, we can do peer-to-peer between the two devices. Alternatively, if they are behind the same switch, but this feature is enabled, then it will go and check the root complex to see if that root complex is whitelisted. So we have in the kernel a hard-coded list of PCI switches that we know can handle peer-to-peer traffic. And it just checks the vendor and device ID versus that list. If it's whitelisted, then it says you can do peer-to-peer. If it's not, it returns an error. By the way, for if you're using AMD systems, then it will check the CPU type and not the PCI switch, and not the root complex type. So after we said that, to summarize, we can summarize what this function requires. It requires to know the PCI topology. It requires to know the ACS configuration of the relevant PCI switches. And it requires to know the type of the PCI root complex, or the CPU type. And the problem is that all this information is not exposed inside the guest OS. So for root complex type, QEMU emulates only all root ports. For the PCI topology is defined by the user. It does not reflect the real PCI topology. In all the cases I've seen in cloud service providers, it has no relationship to the real PCI topology. And the ACS configuration of the PCI switches is not exposed because the PCI switches themselves are not replicated inside the guest OS. So this function is totally broken inside the guest OS. So I have here 3 proposals on how to try and solve this issue. The first proposal is to replicate the PCI topology. And I will first say that this is not my preferred proposal, but a lot of people ask me why not to do it, so I decided to present this proposal anyway. So I try to think how to do it most efficiently, and what I have thought about is to have 2 new emulated devices. One will emulate the PCI root port, let's call it PCI root port P2P, and the other will emulate the PCI switch. So we have here a simplified diagram with all the PCI BDF addresses. And you can see that basically the change that the user will need to do in his configuration is that if he wants to use peer-to-peer, then when he passes this information to the QEMU, he will have also to pass the matching host BDF devices. So the QEMU will know what information to take and what validations to do when it sets up the VM.
Why?
Because, for example, when he defines the PCI root port as a peer-to-peer PCI root port, we want to know that in the host machine we have a whitelisted PCI root port, because otherwise the peer-to-peer won't be enabled. So
unmute, please. Okay. Does that? I don't know. I can. Yes, I think.
Yeah,
I think I
you
might.
can.
So in general, like as a basic rule of thumb in QEMU, we don't avoid you shooting yourself in your foot. So I'm not quite sure why you would necessarily do any sanity checks at all. So the typical path you would take in the QEMU world is that you just say, this is my virtual topology, and then you assign your physical guests in there. And if you, as the person that set up that environment, did that wrong, then, well, it is going to implode. Yeah, sure. But it's you who did it wrong. If you going through these super advanced topology configurations in QEMU, you need to know a lot about your host topology anyways. So you may as well infer that you have found out how exactly your topology works. And the idea then would be that the entity that collects all of that information would be a higher level management stack, such as libvirt. that is able to enumerate that using, for example, sysfs. So you would expose using sysfs that, hey, I have ACS enabled here. I am able to go and create I do know what peer-to-peer traffic is, and this device can actually do that with that device. And then that management stack goes and creates a compatible topology in the guest. And the compatible topology doesn't have to be the same. It just needs to be compatible. But I wouldn't map it to whatever the host does at all.
Okay, so yeah, I thought that if we're going through this proposal, and like I said, it is not my preferred proposal. I'll show you the next one. But if we're going through, I thought that it's better to also validate it and not just let the user, like, basically, you can say, trick the guest OS into thinking that it can do peer-to-peer. But I get your point. That's also a valid way, I guess.
It's not just only it's not just only about tricking. It's also that maybe you want to have the exact same topology with P2P DMA for virtualized devices. What if you have a virtualized RDMA device and a virtualized whatever PV GPU, and you want your RDMA textures into your PV GPU? I don't know, whatever. Completely contract example, but there's a good chance that you want to have a fully virtualized environment that also has peer-to-peer DMA capabilities.
Yeah, I see. Okay. I'm not ruling it out. We can discuss it later. But again, I'll talk about the next proposals, and maybe we can decide actually to do them and not this. Because so just to summarize here, so basically this you asked me why to mention the host BF. So another thing is that I wanted to replicate the ACS configuration, for example. So in your case, you're saying if the user decided to define a PCI switch for peer-to-peer, then we will configure it to have its ACS disabled, regardless if in the host it's disabled or not.
So the basic train of thought is very simple. It's from the guest point of view, it doesn't matter whether you have a device behind the virtual switch, and that behind that virtual switch, it just happens to have two devices that are able to do peer-to-peer. But on the host, it may as well be a much more complex topology. It may be ACS disabled, and then you do actual peer-to-peer between, I don't know, yet another completely like root port attached device and another one that is behind the switch, which is compatible. But because you already did set up all of your windows correctly and all of your transactions correctly on the host, you do know that you can do a much more simplified setup in the guest on a virtual topology, and that's why I would completely disconnect the two.
Mm-hmm. Okay. So
mute again, please.
Yeah. So if we want to validate it, if we don't want to validate it, that's great. But yeah, regardless if we want to validate it or not, we will need to add this new PCI peer-to-peer root port to the whitelist. So the guest OS will find this root port type as a whitelisted. And I wrote here to export this whitelist to a user API file, but that's only if we need to validate it. So the pros of this approach is that this requires minimal changes to the kernel code, very minimal, if at all. The cons, in my opinion, are this will require a modification of existing VM configurations for peer-to-peer setups. I don't know how long that will take and how willing are cloud service providers to do that and validate that. But in my opinion, it's not a minor cost. And if we go to the approach that I presented, that the guest topology should be the same as the host topology, then it might be kind of a security leak information
Excuse me, can you turn on the microphone again? I think it was muted.
Let's see if it.
I can hear you at that speaker.
Okay, you know what?
Yes, thank you.
You want me to probably leave this one?
Oh, okay. Fair. I'll take this one. I was saying a big veto from my side because it's violating almost every layer we have, where it combines device-specific functionality with virtualization, particular implementation details. So we shouldn't have a KVM hypercall that is handled in KVM code, especially. That allows you to enumerate what device capabilities there are. It's going to break a lot of assumption. TCG is going to break users of. Say again?
That was you.
Oh, that's me. Oh, users of Vfio that are not using KVM also probably want to have P2P DMA. So anything that is related to up bar mappings correctly, so you can actually DMA into each other's bars. All of these pieces need to be available to just generic VFIO users in addition to virtualization. You cannot tie it into KVM.
Okay.
Okay. That doesn't exclude a hypercall.
Yeah. Okay. The comment was that doesn't exclude a hypercall. In theory, it doesn't. In practice, there's a bunch of heavy lifting that you would need to do in order to expose hypercalls into user space, because currently KVM doesn't do that at all. KVM terminates hypercalls always in kernel space.
Yeah, but I'm also talking about kernel space. I'm not talking about user space here.
Yes, and that's exactly the problem.
What's the problem? I don't get it. Because the calculation is done inside the guest OS kernel. So.
Oh, sorry, the host kernel.
Sorry?
In the host kernel. KVM hypercalls are terminated in the host kernel.
Yes, and we can and so.
And the host kernel has like should not have any say in guest topology. Guest topology is a user space owned piece of information in a KVM world.
Yeah, well, usually in peer-to-peer situations, at least in situations like I showed, where you have a full box with all these accelerators, like you have a single guest on the machine. It has all the devices anyway, so I'm not seeing this distinction as strongly as you are, I guess. Because you don't want to do scale out if you don't have the entire box anyway. It's
just about philosophical concepts of the way we do the layering in the KVM QEMU world, and that is just breaking them, and it's going to set a precedence that is going to just make that whole architecture fall apart. Either way, I think the first approach was actually fine as long as you remove the host equals part.
Mm-hmm.
But that should work perfectly okay. What I'm interested in is the other pieces that are much more complicated. It's enumerating whether P2P DMA is capable from user space, because you have to have some way to transmit that information into user space. And the other part that is missing
user space
is
of the guest or the host.
Host user space needs to somehow understand, I have these two devices here. Can they talk to each other? How can they talk to each other? Can I establish a link between them? And how can I establish that link between them? And
when do you want to know this information? What stage?
You want to know that stage when assembling that command line.
To the QEMU?
Yes.
But didn't you just said that we don't want to, like, the user, the person that defined the VM already knows what is the box. He knows if he can do that because these are complex scenarios. So
no, I want a tool that executes QEMU to enumerate the hardware and assemble the command line based on that.
Okay.
I want to say, I want to have these two devices attached into a guest using peer-to-peer DMA.
Okay.
And
now
then your tool should find out all the rest on how to do it and tell you yes or no.
Okay, I understand.
Yes.
It gets a lot more complicated because the current situation is we have the subsystem in the kernel called PCI P2P DMA that has the calculation we've been talking about. And anything that uses that is not going to work in a VM. However, VFIO doesn't use it. So Vfio quite happily plugs in broken P2P configurations into VMs or working ones or whatever. So looking forward, I would like, well, IOMMUFD to call the calc function, right?
Yes,
So
that's the plan.
right, so it will call the calc function, and that means QEMU will fail the IOMMU mapping somehow. And I don't exactly know how this is going to work, but that's kind of what's in my head right now is you will not be able to get a peer-to-peer mapping set up in your IOMMU if the calc function says you're not allowed to do it, which means that QEMU has already kind of discovered that it's got a problem because it's gone and created a mapping, it's tried to put things in it, and it's got a hole in that mapping. So should QEMU just leave an unmapped section and run the guest if that's what it's been asked to do, or should it build topologies? I don't know. But it does have and could have the information.
We need to think about compatibility.
Oh, that's Alex. He's on the phone.
Oh, Alex. Hey, sure. Keep going.
Yeah. So QEMU could know that information, but we have historically been allowing it regardless of whether it works. So QEMU could know that it failed and decide whether or not that's a critical failure path or not. But how do we make it work with existing QEMU?
Okay. Making peer-to-peer DMA. Are you hearing me again?
Yeah, we hear you.
Well, just because we hear the mic doesn't mean the.
Yep, you're good.
Is it on again? Okay,
You're
very good. I just don't see it on the screen here. The QEMU. How does peer-to-peer DMA work today in QEMU at all? Given that usually if you want to do peer-to-peer DMA, you would DMA into a bar region of another device. How does the guest know that it is the same? Like how do you even? Okay, sure.
So it works today because in a QEMU environment, it always goes through the IOMMU. So we need to have the switches with ACS turned on and all those other features. And the QEMU uses Vfio to plug in the bar mappings into the IOMMU. And this is another sore spot where it uses the follow PFN security breach problem path to do that. So it directly extracts, so the flow is Vfio PCI will mmap the bar space into QEMU, which will then stick it into KVM. Then it will map that bar space into the IOMMU using follow PFN to discover it. And then from the guest perspective, it's got a chunk of KVM memory that one-to-one matches the IOMMU map that points to the bar. And because we have ACS turned on, all the transactions go through the host. And so they go through the IOMMU translation and everybody's happy.
So it's not really peer-to-peer, you're still punching through the IOMMU.
Okay, so that's the configuration, okay? And then so to make this all actually useful, we have to bypass the ATS.
Yes.
So to bypass the ATS,
then you need to go and have the same mapping.
The preferred approach is to use ATS.
Yes.
So we use ATS on the initiator, and then we issue an ATS translated transaction on PCI, which bypasses the ATS violation, the ATS enforcement on the switch because it's already been translated.
So the first transaction will always go to the host bridge, will get translated, and then using the ATS, you will cache that translation, and the next transaction will go with the translated address. And then if your ACS configuration is turned off, then it will do actual peer-to-peer without going into the host bridge again.
So the whole thing is an incredible, painful mess, is the answer.
I'm trying to wrap my head around how you have completely. We can also use two mics. Too. Yeah. We just go to the back of the room. The thing I'm trying to wrap my head around is how all of that works with fully virtualized, like with a completely different address space map. If you don't do translation, but you're basically saying you always do translation, which means you have to do ATS.
Yes.
At which point you have a super big security breach because ATS basically means you have to trust your hardware altogether because your hardware.
You always have to trust the hardware.
No, not if you use an Iommu.
No. What PCI defines that special ATS pass where you can set the translation not required bit and all the switches forwarded directly. That's baked into PCI.
Oh, geez.
There is no trust the hardware here, right?
Okay.
You always have to trust the hardware. You have to trust the hardware to issue the TLPs with the correct RID, right? We trust the hardware in this model.
Yeah, fair.
And like I said, the classic configuration is that the guest OS has all the devices in the system. It's like, I don't see, like, you can do peer-to-peer if you divide it into multiple guests, but that's just not cost effective, I guess, for anyone to do. Like, you first do scale up inside the box, and then you will do scale out to multiple boxes.
So you didn't have another proposal here.
I had another slide. So instead of
I was going to say the simple version is we just add a kernel command line that says peer-to-peer works, and the calc thingamajig that we're talking about just says true, right? That's like the simple solution here, because as Oded has said a couple times, the number of people that actually need this is a teensy bit small. And it would be very easy for QEMU to even push that.
So you're basically saying if they're going to point the gun at the toe, let them shoot it.
It's a thought. I mean, the building the PCI switches is similar, and we've done things like that before. But the current situation is all the people doing this don't call calc in the first place.
Correct.
So, you know.
So that's how we do it today. We just don't call the function.
We just don't call the function, right?
Yeah, but that only works if you use DMA buffer. If you use P2P DMA, then like with a file system device, then you can do it because it's inside the kernel. It's not in your device driver.
Yeah. So I mean, the goal from the kernel perspective is we want everybody to call the function. Like I said, we want Vfio to call the function. We want all the DRM drivers. We want everybody to call the function because it exists for a good reason. But we still need it to make it doesn't work in VMs. So. And I guess the question is
I had a last proposal which is similar to the hypercall, but instead of a hypercall, define a Vfio device that the guest can inquire, and then the host will do the calculation. So instead of a hypercall, do a Vfio device that basically does that. I don't know if that's more acceptable or less acceptable.
It certainly goes through user space, which is better than terminating in kernel.
And then we will, in this solution, we will need, because it goes to the user space, we will need to expose this calc map type and this function as some kind of a user API for the QEMU to figure out if the two devices can do peer-to-peer or not. I don't know if it's fun. It's better than in layering terms.
If we just go back to the first proposal and you have QEMU say, I want to do peer-to-peer between this device and that device. If you have that knowledge, and you can then just tell Iommu I want to do peer-to-peer DMA between these two devices. Please do that now. And it tells you, no, I can't. Then you have a message from the user that says, I want to do the peer-to-peer DMA. You have Iommu that tells you, no, I can't. And then you can fail. And then you don't break any ABIs or any contracts that you have.
But in the first proposal, even if the user will tell us, we will need to expose to the guest some kind of topology that will pass the calc map type in this function, right? We will need to set it up correctly.
Yes, and the Vfio PCI device node can find that out because it is a downstream of peer-to-peer enabled devices. So that gives you the hint that says, I want to do peer-to-peer DMA. And then Vfio PCI finds that out and automatically makes sure that all the mappings are configured for peer-to-peer DMA enabled. And if that doesn't work, then tough luck.
Yeah, I mean, it sounds simple, right? You just need to put a PCI switch in and turn on ACS, and then it'll pass the test, right? So just have QEMU make a PCI switch and turn off ACS.
Yes, that's what I said.
That's it. Yeah, what he said. Yeah, so it's kind of like a combination of 1 and 2, right?
Okay. I guess we can talk about it later more.
Yeah, it's a lively discussion. So
yeah, sorry,
but unfortunately, time is up.
Okay.
Maybe you can continue it later in one of the meeting rooms.
Yeah.
Okay. So the next session is. The next session is from Yikong Yang about integrated PCIe monitoring and tracing facilities. He is participating remotely, so.
Hello, can you hear me? Okay, I'm trying to uploading it.
Looks good. Yes, we can hear you.
Yeah. Okay, I think I have successfully uploaded my slide. I'd like to have present and discuss new technology introduced in Hasilic's latest quantum server, which is called the Integrated PCIe Monitor and Tracing Facilities. Something rather specific to the PCIe stuffs. I'd like to start this in the following aspects. The first one, I'd like to introduce for why we have these facilities, and then overall view for the PCIe MU and the usage. Then is an introduction for the PTP and the usage. Then I'd like to speak something about the potential scenarios for this, we assume, and some open questions I'd like to discuss and seek for suggestions and comments. Like something, how can we make it more helpful to both software and hardware developers and get more people involved? So we have some questions why we need this. The first thing is why we need this. Since we are currently lack for some, or we have limited PCIe link analyzing and tuning method. We have some various tools for monitoring and tracing the CPUs, but almost none for peripherals, especially for PCIes, which is currently lack for now, like something to better monitor the link status and profiling the utilizations for the PCIe. There is a limited method for debugging PCIe link. The common PCIe analyzer is expensive, complex, invasive, and sometimes hard to set up. Then if the performance is not optimized since we deploy the same configurations for all the cases, like buffer allocations. It is unchanged after booting up for all the scenarios, but the different I/O applications are on different stage of the same applications may vary. They may get different performance when we change these configurations. And how do we try to solve this? So we introduced integrated monitor and tracing facilities. We have implemented 2 PCIe IEPs on our newest SoC, which is called PMU and PTP. With all of this, we will be able to further improve the monitoring and profiling abilities for our SoC. Since we already have on-call PMUs for DDR interactions and etc. This time we bring it to the peripherals like PCIe PMU. Then we bring a lightweighted PCIe analyzer-like tracing facilities for tracing and recording the TLP headers. It is embedded in our controller. So this will ease and improve the PCIe analyzing at the package level. Will be more convenient, quick to set up, and free. Since it's embedded, you do not need additional setup. Then we have one experimental but a creative feature. That is, we provide interface for tuning the PCIe link configuration dynamically at the runtime, make it possible to optimize the performance according to the scenarios and applications. Then I'd like to have introduce of the PCIe monitoring unit and the usage. So the left figure shows that the composition of our root complex is look like. It is composed of several components. several root port and several endpoint. Each root port and endpoint are composed in one PCIe core, on which on every PCIe core we have one PTT device and one PMU device responsible for monitoring the link activities on the core it locates. So the link activities and the utilizations are denoted as different link event. So we have several counters for monitoring such link event that like bandwidth, latency, and fast utilizations and buffer occurrence. The PMU also supported to statistic these counters conditionally. We can decide, the users can decide to filter the statistic either by the certain package length or the event from certain root port or the endpoint. So the usage is rather simple. We can use the monitoring can be configured and started using the general perf tools, which is rather general in the Linux. So the support for the perf tool is also appear in the main line. The usage is rather simple. You can start the monitoring by the perf state command. Several processes you need to make. The first one is to specify the PMU device you'd like to use. Like this, the has PCIe 0 core 2. You should use the device where you need to trace in your link event. For example, you like to trace in the root port 0, and the root port 0 is monitored by this PMU device. You should specify it correctly. Then you need to specify the event you'd like to monitor, which is called the link event in this command line. We exposed several link events like memory read count. Okay, how many memory read performed, and how many dword of the memory read we have performed on both directions, inbound or outbound, and something like the latency of each memory read or memory write packets. Then you can specify the filters, which means you can filter the event you'd like to monitor from either root port or from either one certain endpoint. You need to specify the target filters. Except two commands. One is the port, or you can specify the BDF, which means the endpoint's BDF you'd like to monitor. Another two command is provided for you to filter the TLP packets, link event you'd like to start the trace, or only the event you'd like to trace, you'd like to monitor. One is called the trigger filter, which means you can trigger when the certain TLP event, when the certain TLP length is match your expectation. For example, if you specify the trigger mode as 0 and you specify the one trigger length as n, then when the first TLP packet length is greater than the ND word, will start the trace. Another thing then is the threshold filter. You can only monitor statistic the event of certain length of TLP. Below figure is provide example. In this example, we're monitoring the memory read packets, the total memory read data length of the inbound directions for 10 seconds under the port 0, under the port 1. A network card is mounted under this port, and during the period it is performing the iPerf process. We can see that we have around 6,000 counts of this event, which means we have monitored in that 6,000 counts TLP packets that is match the filter we specified. Okay, that is for the PMU side. Another IEP we introduced is the PCIe2 and the trace device. Like to the okay, somebody is going to ask. Oh no. Oh, like to the PMU device, we have one PDD device for each core, responsible for tracing and monitoring the tracing and tuning the PCIe link on the core it locates. It has two functions. One is for tracing the TLP packets. We only record the TLP header. It can be set to trace for the TLPs downstream the certain root port of certain requester ID, which means from the certain endpoint of the root port, which matches the requester ID reside, and also can be filtered by the certain type. We can choose to trace only the packets of posted TLP or non-posted TLP or completions, or all of them or both. Another thing is that we can filter the TLPs to trace by the certain directions, inbound or outbound. Another feature besides the TLP tracer is dynamically tuning the link configurations of the PCIe core. So we export the PCIe link export the PCIe link configurations to the users by the device. Then the users can use this to tune the link configurations at runtime after the system is put up. So the usage for the PTT trace is similar to the PMU. It is also we also make use of the Linux perf2. We can start the trace by simply specify the perf command, perf record command with specifying the target PTT device, filters, TLP types, and the directions, and the desired data format. No other configurations or setup from the hardware is needed. You just put up the system, and if you want to trace the TLPs from the certain link, you just use the load the driver and start the trace by the perf command. So when starting a trace, you need to the first thing is to specify the filter, which means the source of the TLPs you'd like to trace. It's the first command in this example. You can specify the filters by you can specify the root port of the TLPs, which we can filter the source of the TLP packets. Then you can choose the desired TLP types, like posted TLPs, non-posted TLPs, or completions. Yeah. Then is the directions. Just specify the option directions for the desired TLP directions you would like to trace, either inbound, outbound, or both. The last option is the format. It is something related to the headers storage. We provide two format of the traced TLP headers. One is 4D word, another is 80 word. So unlikely to the PMU counters, we need additional support for the perf2s to enable this function. The patches of the perf2 support is still under reviewing on the line. So when we get the traced data, the users can also use the perf2s to do the data display. So this slide shows that the raw data formats look like and what users will get from the perf2s. The left two figures shows the raw data format, which means the TLP headers directly traced by the PDD device and stored in the memory. So one is the 4D word format, and another is 8D word format. So the 8D word format treats and stores the whole headers with some additional information. So it will certainly consume more memory. For one packet, 4D word data consume half memory compared to the 8D word. So it will be more friendly to the storage. As a cost, it will provide reduced information, not the full information from the headers. The data field traced can be directly mapped into the PCIe specifications definition of TLP packets, which means the traced data, the field in the traced data is definition is the same with the PCIe specifications. So for the 8D word format, it's totally the same. But for 4D word format, just part of the headers is reordered, which means the field may not totally follow the orders of the definitions in the PCIe spec, but the definitions is the same to the PCIe spec. So luckily, users don't need to remember this. We make we have support the perf tools to help to decoding it. So just to use when we got the trace data by the perf record command, we can also use the perf report command to do some decodings and display the data. The command is show on the bottom, and we'll get the decoding and displayed by perf report on the right on the two right figures. Okay, one is 4D word data format, and another is 8D word data format. The raw data is stored as a binary blob by the perf tools, and we can make it more friendly to the human as the perf report tools. So, but for now, currently only a minima decoding support is added as shown. It may be more helpful to decode every field of headers according to the spec, but it may take some more works, which is currently done now. Instead of using this, users can also try to decide to decode or handling the data by a custom script or tools by itself if the provided perf report tool is not met his or her demand. So another thing is about DMA implementation of the PTT trees. We have one hardware comparator in the PTT device for the trace modular. So the PLP header tracing is implemented by the hardware variant and the hardware comparator. So merely very little overhead for this. Additionally, we deploy 4 DMA buffers for the PTT trees. Act like a ring buffer, as shown in this 4 buffers. The TLP headers will be stored in the buffers one by one, then read back until the trace is over. When one buffer is full, it will notify the drivers by the interrupt to consume it. The driver will commit the buffer, the trace data to the perf aux buffers, which will finally be exported passed to the users as the raw data. So it is deliberately designed to have 4 DMA buffers, which each size of the DMA buffer is greater than 4 megabytes. So we won't miss one packet even on the full device, because it is calculated by the hardware guys that we need at least 4 megabytes DMA buffers with 4 tons of DMA buffers for not missing one data. So by this design, the tracing should be reliable and won't affect the traffic significantly, since we have very low overhead and we won't miss one packet we'd like to trace. So another thing is about PTT is the tuning function. That this slide shows how tuning is used, implemented, and how to prevent corrupting the PCIe traffic. The link event, which is also called, okay, you can just regard the link event as PCIe link configurations, are exported as sysfs attribute, shown in this in the first column. Currently, we support tuning the queues of the certain TLP packets, posted, non-posted, and completions, and the buffer level of certain directions, inbound or outbound. The usage is rather simple. You just, if you want to know the current configurations, you just read from the sysfs attribute of the certain event you'd like to know. And if you want to changes, you just write one value to it. The value of the tune event is an exported to the users is an abstract level, like 0 for a low level of certain event and 2 for a rather high level for certain event. The real root complex configurations are hidden behind the levels and beside and read indirectly with the assistance of the Iommu. Iommu means the intelligent managed unit, which is just like some coprocessors on the SoC. So when the users set one event, the drivers do the necessary check and then set the event and the data to the hardware registers. The hardware register will signal will have an interrupt to notify the have an interrupt to notify the Iommu to process the command. So then the Iommu will read a event and read a command, then try to map the abstract level to the real PCIe root complex configurations and then do the config. Finally, when the configuration is done, it will clear the interrupt status and notify the drivers. By this time, the driver is still pulling for the completions, pulling the interrupt status register. When the interrupt is cleared, it knows that the configuration is done. It will read or read the result or read the values and notify the users. So with this DLAN, we assume that the tuning will be safe and will prevent the random settings from users to corrupt the PCIe Inc. Since both the drivers and the users are not setting the PCIe root complex configurations directly, it is doing this with the assistance of the Iommu, which is not seen directly by the users. But now we only provide the abilities to tuning the PCIe link.
Kong, we can't hear you anymore. You probably have some transmission problem. Oh, yeah.
Okay, can you hear me? Network is not
Yes.
stable.
There's still some jitter, but we can hear you. And I think it's gone again, so yeah. We currently can't hear you.
Hello?
Now we can hear you.
Yeah, okay, but I cannot handle my slides. My
one
still
second.
presenter. Ah, okay. I can do it now. Okay, so the next part is that potential use scenarios we assumed. So we assume some potential use scenarios for our monitoring and tracing facilities. The first one, of course, is monitoring the link status and the utilizations for profiling the link status and for some IO applications. Another thing is about tracing for validating, monitoring, and more some more detailed informations compared to the PMU. Okay, since I read. Okay, do the tracing for the validating and monitoring for a quick and more convenient method, like finding the hardware bugs, for example, out of order TLPs, track the access order and help debug the drivers, try to figure out whether to use, whether the command issued by the driver is as expected, whether we need a barrier or not, and also help to do the error locating and handling, complement to the AR setter, since the AR only captures the headers which incur the error, but we can, by using the PPT trace, we can also trace the context before and after this error packet. Another thing is about tuning the PCIe performance. Try to tune the PCIe link performance according to the monitoring and all the tracing statistics. So if for one certain IO applications, if the users already know the pattern, then just tune it directly. For example, for certain cases where there are a lot of completion packets, try to increase the completion packets weight of the buffer on the link. Otherwise, in most cases that the people may not know the patterns of certain IO applications, then try to monitor the link statistics and tune accordingly. Like by either PMU or PPT, or using both to try to profiling the IO applications pattern, figure out the TLP portions or the composition of each type, direction, and monitoring the buffer utilizations. Then try to tune the corresponding configurations on the PCIe link, and then monitor it to see whether it meets your expectation. So here I give one examples how to tune the PCIe link combined with PMU and PPT. So this says is an examples and how can it resolve. So I use a rather simple application here, copy a 4 megabyte data to a remote server through a PCIe network card. And how can we try to tune this? First, I try to monitoring the IO applications, monitoring the link buffer allocation status. We monitor the counts of how many times the buffer is successfully allocated to each directions, as shown in this perf state command. The event code 9 for the inbound buffer allocations and the event code 109 for transmit buffer allocations. From the perf statistic, we can see that in the situations, the successful count of the the outbound direction is a bit low compared to the inbound directions. So then, when I got this information, I use it as a feedback to tune the link event. So I tune the link event by directly writing to a rather high level to the TX allocation buffer level. The buffer allocation level for the outbound, so the higher, the more likely to get the buffer and redo the remote copy. After tuning, we can see that the counts of the outbound outbound buffer allocation increased. Previously, we only have 6,000, but after the tuning, we have around 7,600. The count increased apparently. So in this, this is a very simple example to show that our conception of tuning the PCIe performance by use of both PMU and PPP. In this example, we see the link activity changed after changing the configurations. But something to know that this isn't a guide for now, that tuning certain configurations can get the performance improvement. It is because that the real cases are complicated and involves many aspects. A single point may not help. So it's better for the user to profiling and tuning repeatedly until achieve the expected result. So last, finally, I got some open questions for these facilities we introduced. I'd like to discuss and willing to hear that your feedbacks and suggestions. The first one is that we really need some feedbacks for the design usage and our future plans, what we want and what will be more helpful to make this more helpful. Since I don't think we have found that some similar technologies and devices like this. We bring it. I think we bring it in the first time. So
have a look at the chat. There were some questions that people were discussing when you were presenting.
Okay.
I'm just wondering. This is very specific to your performance monitor hardware. Is it possible to expand this to pull this information from PCIe switches and other facilities that are already available within systems?
Oh, okay. Currently, it is very specific to the SoC. Yeah, it is implemented in our SoC, but like I write here that for the open question that is it possible for more platforms and devices to expand this to other cases, not for SoC only. Like we have something, we have PMU or PTT for a switch, which can be plugged in, and for network card that can be plugged in. We already have PMUs for our Hasilinko's HNS3 network card, but it's rather specific to the vendors who will provide these facilities. For now, we only implemented in the controller side of our SoC, so cannot be found on
There
other.
are a few. Sorry. Hey, Yukon. There are a few exceptions. So CXL has a standards-defined stuff for this. Unfortunately, not yet from PCI. There obviously are switches out there that do. I've not seen anyone do tracing, but they might. I mean, it may not be documented. But there are definitely documented PMUs out there for a number of different switch vendors. And it would be great. Usually they have weird and wonderful user space tooling. And it would be great to try and pull it into the framework. Ideally get them involved in it. But I mean, it's kind of the nature of perf stuff is you tend to share what it looks like in user space, and everything under the hood is different per vendor. So if we could get towards that, it would be helpful. And obviously beat up your favorite PCI SIG representatives if you want anything standardized.
Yeah, I want. So, if we have one specifications for this, like a CXL PMU, we are more likely to extend it and get more vendors involved. So I mentioned that here. I think similarly to the CXL PMU, we can imagine something like the specification for the PCIe PMU and also for the trace facilities. But trace is more, I think it's more challenging that different vendors may have different implementations. But yeah, I think for the PMU, it is more likely to be possible. Yeah. Also, besides of the hardware specifications, we can imagine something like a software frameworks with, if we have more and more vendors found this useful and get involved in this and provide these facilities embedded in their either controller switch or in their independent endpoint card. Yeah.
I mean, if anyone is interested in standardization and wants to reach out to me, I can probably at least find the right people and build some connections on that. So that's Jonathan Cameron speaking. Or reach out through Yikong, he can get hold of me.
Okay, one question. That is, you mentioned that tracing for the CXL. So for the current CXL implementations, I think they share the some of the physical link with PCIe. So currently, we only in our implementations of the PTD, we're only tracing the TLP package, which is some kind very specific specific to the PCIe stuff. If we extend this to the some lower layers like the DLLPs or even lower, we may have a chance to also. I think is it possible for us to have a chance to also trace the CXL transactions? Yeah, I think that would be possible.
Yeah, it's doable, but it's again, it's a custom. It would be the high silicon version of it. What would be interesting would be at least to look at things like standardizing the trace format, so that if it's dumped by entirely different hardware, at least the fields are in the same order, or exactly what is logged. That would be very helpful. Anyhow, I think given Jörg is looming, that he may have something to say about being out of time.
Yeah, I think it's time to wrap the discussion up. It was very interesting. Thanks, Yikong. And with that, we've also reached the end of our microconference. I want to thank all participants and all speakers, either in person or also our remote attendees. I think it was a great event. And see you on the conference or online. And yeah, have a nice rest of the conference. Bye.
Thank you, everyone.
Bye. Thank you.
Thank you, Jörg, for facilitating as well.
you.